Hi, this is Lika Guhatakurta from NASA headquarters at my home in Maryland. Gives me great pleasure to introduce our first speaker and start the second day of second Eddy Symposium. And Gavin Schmidt, our first speaker, is absolutely a very suitable candidate to talk actually about, some of the research that Jack started way back when that you heard about yesterday. Gavin Schmidt is a climatologist. He's a climate modeler and director of the NASA Goddard Institute for Space Studies in New York. And I think he's been holding that position since Jack Hansen retired, probably like around 2013-14 timeframe. He's not only a scientist of some renown, but also he's a co-founder of the award-winning climate science blog, Real Time. And that's really significant when we try to introduce a complex topic like climate that have so many implications. Gavin has recently been named as NASA Senior Advisor to the NASA Administrator on Climate. In that capacity, he also interfaces with the White House. And without, one other thing I would like to add is that Gavin's early years, he was trained as a mathematician, probably the truest language we all learn, especially in its application to science. And since then, of course, he's done a lot of work in the world of climate. His topic is from paleoclimate to high energy physics, solar drivers of multidisciplinary science. Take it away, Gavin.
Thank you very much. That was overly generous, but I don't have a huge amount of time here. So what I thought that I would do would be to kind of by way of a little bit of the stuff that I've done or that my team has done on solar forcing of climate change, just kind of give you a sense of how multidisciplinary the science becomes very, very quickly when you start working on these kinds of topics.
We lost audio.
Okay, after that small interruption, so I just put this graph together recently, and the idea here is just it was just the thought was, okay, well, I'm mostly working on climate change, but obviously I'm interested in the solar forcing of climate change, and then I was trying to piece together all the different things that we had to learn about in order to make progress in that realm, and it all starts with the history of observations of the sun, and particularly things like Galileo's drawings of sunspots going across the face of the sun very early in the 17th century, and you can contrast that with direct observations of the same things now, and that kind of constancy, but also the changes that have happened since the 17th century are a fascinating part of history. And pinning those things together, trying to work out what it means for solar activity to have such a long time series of different things, whereas we only have very short time series of the observations from satellites, means that you have to pull together lots and lots of very difficult and different disciplines. I mean, the work just putting together the sunspot record is very much one of historical documentary. You have to go back, and people have gone back and looked at the original drawings, the original notes, the original thing, to try and construct a statistically stable methodology for constructing the sunspots. And that's still a work in progress. Other kinds of indicators of solar activity, such as the geomagnetic indices, they require people who are following geomagnetism. That's a whole different field than people who are following what's going on the sun. And then, the more recent methods of following neutron counts, which exist because of high energy particles coming from somewhere in the galaxy, impinging on the atmosphere, creating a whole cascade of high energy particles, including muons, which then end up creating neutrons when they get closer to the ground. All of those things, those cascades, all of which produce as well cosmogenic isotopes, which then go into the archives of ice cores and ocean sediment and the like, which gives us an even larger and longer view on what's going on. Each of those fields is a very specialized, long-lived, different field from all the others. And there's very few people, in fact, probably nobody, who understands all of those things at the level that's required. And so just building a record of solar activity requires, just before you even start, multiple disciplines, multiple practitioners, and deep, deep collaboration before you can even get started. But then a lot of these things still need to be calibrated. We have a sunspot cycle, we have these cosmogenic isotope changes, but what does that mean in terms of the physical changes that we want to put into a climate model, such as the total solar irradiance or the spectral changes in solar irradiance? We need to have calibrations. And so we need to, and historically, we've reached out to astrophysicists to help us with that calibration. And this is going back 30 years now. And it's interesting for a couple of reasons. One, this paper, which was a 1990 paper, tried to characterize sun-like stars as whether they were cycling or non-cycling, and they seem to have detected that the non-cycling ones were slightly less bright than the cycling ones, and therefore that gave us an astrophysical calibration for what a grand solar minima might produce in our own sun. And it's interesting because Robert Jastrow was the head of GISS until the 1980s, when he was replaced by Jim Hansen. And by this time, by 1990, he was actually an arch climate skeptic and was very involved with the George Marshall Institute and writing some rather dubious things about climate change. But for a long time, this was cited as the best calibration that we could use, and the models that we ran through the early 2000s all used this calibration to try and estimate how much solar change had there been since the Maunder minimum, for instance. But unfortunately, with more data, with more observations, with better statistics, this idea kind of evaporated, unfortunately, and is still something that we're looking at. People are spending a lot of time looking at sun-like stars to see if we can find a pattern that would be translatable to the history of our own sun, but that seems not to be as easy as we thought it was going to be. Now, the mechanisms that are involved when it comes to driving change on the Earth from changes in the sun are related to chemistry. They're related to atmospheric dynamics. They're related to aerosol physics. They're related to cosmogenic processes. They're related to ozone processes. They're related to all of the different things that are going on at the surface of the ocean. And even just putting these things together requires multiple levels of expertise to do any of this justice. But there are a couple of other things that are interesting about solar science. And one of the things that you might not have thought of as being a key new discipline that you would have to think about when doing science like this is sociology. And the reason is that because of the complexity, because of the varied sources of data, because of the statistical issues with that data, because of the uncertainty in that data. And I think perhaps a long history in various cultures of seeing the sun as paramount. This is a picture from the Egyptian Museum in Cairo, and it's from Tel Al Almana, the city created by Akhenaten, who was perhaps the first monotheist pharaoh who devoted all of his energy to worshipping the sun, of which he was, of course, the ultimate personification. So possibly just ego rather than solar worship. But we have this history of looking up at the sky and seeing the sun and thinking, well, everything must be related to that. And when you combine that with an understandable aversion to having to deal with the fact that humans are changing the climate and that actions that we are taking are having an impact on things that we care about. People don't want to hear that. And when it comes to such a transdisciplinary topic, there are people who will contrast these two things and say, well, it must be the sun because we don't want it to be us. And the sociology of climate skepticism or contrarianism or denial is something that I did not anticipate 20 years ago that I would become an expert in, but I think I now am an expert in. And that leads to this kind of stuff. And people, I went back to my office yesterday, started to sort through my mail. And, you know, there's a whole pile of magazines that people have sent me. There's a little bit of personal correspondence, but almost all the rest of it was packages of very deeply felt crank science about climate change, about the sun, about the universe, and about our role in it. And some of them had some great stamps, so I took the stamps off. But this is a real thing, and anybody that works on this topic needs to know something about these folks and what makes them tick. It's very interesting, but you know, you might be tempted to say, well, you know, conspiracy theories and you know, and the complexity. But you know what? My graph is as complicated as the one on the back of his wall. And the links that there are between all these different things, from high energy particle physics to paleoclimate and aerosols and remote sensing, there's a lot of space there for strange and unexpected connections. And I would not say that we have found the last of those strange and unanticipated connections. So with that, let me lead you on to the next sections of your symposium. And I thank you very much, Lika, for inviting me to give a very brief introduction.
Thank you so much, Gavin. This was short but pithy. You know, not everyone is a sun climate practitioner. There are a lot of interdisciplinary scientists, so you captured it really beautifully. Erica Palmero, she's the one who is monitoring Slido and now going to provide you with some questions. We would appreciate for you if you could stay online. There might be more questions later, but you can join anytime you have the agenda. So with that, I'm going to ask Erica to take control.
Yes, good morning, everyone. So I don't see questions on Slido at the moment, but so please go ahead and ask your questions. But in the meanwhile, I received the one question off Slido, and I will ask it. So Gavin, do you think that the sun is a small player in modern climate change, which was a conclusion that was reached in the latest IPCC or Intergovernmental Panel on Climate Change?
Yes, I do. If you look at the attribution of the long-term trends in climate, you can look at what's happening in the ocean, at the surface, in the troposphere, in the stratosphere. You can see the fingerprints of solar change. You can see them very, very clearly in the upper atmosphere. It's a little bit, not quite so much in the lower stratosphere, in the lower atmosphere. But the long-term trends, they're all being driven by increases in greenhouse gases and other anthropogenic changes. And the complexity of those fingerprints and the matches to the observations make that an unequivocal statement.
I have a question. I guess I'll take the chair's prerogative, and that is, and forget my pun, but how do we shed some light and resources onto the woefully neglected sun climate research? I think your graph that actually indicated kind of the level of data we have from short period to long period, lack of calibration. How do we bring more energy and focus into that? You are in an important position now.
Yeah, kind of wearing my kind of NASA strategy hat for a second. One of the things that NASA does really, really well is very pointed and deep understanding of single sets of observations, and we produce massive amounts of very, very high quality observations across all the different directorates that NASA has. What NASA does not do very well is really try and integrate those directorates and those observations outside of their silos. And while, obviously, the climate people in SMD are using information from heliophysics, and we're working with people who are working on, with planetary science on exoplanets and other stars. We don't have a very integrated way of creating teams and pushing people to work together to kind of delve into the more subtle aspects. It isn't that heliophysics just exists to produce one data set or two data sets that then can be used for other people. There's more to the potential calibrations and potential collaborations that we can have there. And I think that one of the things that I would like to see happen is more, I mean, it doesn't need to be huge, but places and means to foment inter-directorate connections that are more than just a one-off, or that are more than just, you know, one person who knows somebody else. You know, that we institutionally try and create the space where multi-directorate, multidisciplinary science can flourish.
Thank you so much, Gavin. You know that we are running a little bit over time. We will reach out to you, stay online with more questions and perhaps dialogue also with our early career professionals. And I'd like to introduce our next speaker now. Next speaker is Justin Casper. And many of you might actually know Justin already. I have known Justin when he was actually a young graduate student back in Boulder, Colorado. His passions are exploration of the solar system, sensors, and spacecraft, and using nuclear power and technology. And that's kind of a newer passion. He's still building on this technology side to make the world a better place. He's been at Harvard, and then he's been a professor at University of Michigan. And very recently, he's the Deputy Chief Technology Officer at BWX Technologies. He's also actually, he's not only playing a very prominent role in NASA's flagship mission Parker Solar Probe, being the youngest PI, I think, that heliophysics has ever selected at least, but he's also PI on a new mission called Sunrise, which actually is the first radio array in space and instruments that's going to be looking at the sun with radio observations. And without much more, I would like Justin to start his presentation. Justin will be given the same amount of time he was promised. Please go to Slido, ask your questions, vote on those, and Erica will be joining in with the questions. Thank you, Justin.
Well, thank you so much, Lika, for that lovely introduction. Yeah, it's been I think it's been at least 2 decades now. And as maybe someone who's moved successfully into a later phase in their career, I just want to acknowledge all the encouragement you gave me when I was a young scientist. That made a big difference. So what I thought I'd do today is touch on data analysis issues, data processing challenges and opportunities in my experience in space missions. And I'm going to focus on the Wind, Parker Solar Probe, and Sunrise missions that Lika just mentioned. There's a graphic of Wind on the left that launched in 1994, a graphic of Parker Solar Probe that launched in 2018. And this is our Sunrise mission, an Explorer mission consisting of 6 spacecraft that should be ready for launch in the summer of 2023. Oh, you can't see it? Oh, you know what? Hold on. How do I, hold on. Hi, everybody, I'm back. Sorry, I didn't realize I had to click screen share too. So here's the 3 graphics I was mentioning: the Wind Spacecraft, Parker Solar Probe, and Sunrise. And I'll be talking about all of those. What I thought I'd also do is I'll talk about them in that order because it kind of takes me through my career in heliophysics to date. So I started working on the Wind Spacecraft back when I was a graduate student, then a postdoc. And eventually, I think just because I spent so much time analyzing the data from the Faraday Cups on Wind, I got appointed instrument lead for the Wind Faraday Cups. And I'll try to give you a couple examples of some of the work I did, both that I think was cool work, but also involved saying, you know, let's transition from looking at individual events passing by the spacecraft and try to do statistical studies with large data sets and see what kind of cool physics we can do that way. So I'll show you a little bit about plasma instabilities, variation in the solar wind helium, figuring out how ions are heated in the solar wind as examples of that. And that'll be the bulk of the talk, but I'll talk a little bit about Parker Solar Probe, which with my experience on wind and doing some technology development for surviving an environment close to the sun, I was fortunate enough to become the Plasma Instrument Suite Principal Investigator. I'll talk a little bit about the mission and give you an example of a machine learning technique that we recently published trying to keep up with the volume of data solar probes producing. And then I will talk a little bit about Sun Radio Interferometer space experiment. Now, we don't have data yet. We're a couple of years out from launch readiness. But what's key to making Sunrise work is some really precision position and timing information. So I'll show you how a new kind of data collection makes a big difference on that mission. Lets us reduce the data that we need to send down to the ground by more than 4 orders of magnitude, which is what let the mission happen. And I'll also talk a little bit about our operations concept, because unlike other missions I've worked on in the past, we're actually doing the mission operations and the science operations on the cloud, which I think is pretty novel. So part 1, wind. So there's that picture of the Wind spacecraft. There's a photograph of wind, so you can get a sense of its scale relative to a human being. Interesting things about the Wind spacecraft: it spins once every 3 seconds or so. So it's got these really long wire booms sticking out that measure electric fields and radio waves. There are magnetometers on the ends of booms, and then there are plasma instruments on the side of the spacecraft, including the Faraday cups that I've worked on for most of my career. So as the spacecraft spins, that's useful for 2 reasons. One, each plasma instrument gets a view of every direction in the sky. So you're able to sweep out the 3-dimensional distribution of how many particles in the solar wind of a given kind are moving at a given energy in a given direction. You can make these 3-dimensional maps of the velocity of the particles. You can also do a really good job calibrating the instruments, because the spacecraft spinning, so you can figure out little subtleties in the calibration response by seeing spin-dependent effects. So here's just a little graphic showing some of the instruments on wind. I'm not going to go through every single sensor in detail. I just want to call out one of the things that I think has made wind a particularly impressive heliophysics mission, which is there was a ton of redundancy. So a lot of modern missions, I think a direction we're trying to go is don't try to be perfect. Be good enough, but then build multiple spacecraft and learn measurements from, do science by having multi-point measurements. Wind is of an era where we had beautiful instruments, but also instruments that overlapped. So we have like 3 different ways of measuring the electron density. We have 4 different ways of measuring solar wind ion properties. And so over the course of the wind mission, by studying the response of those different instruments, we have a beautiful understanding of the calibration of the instruments and the precision of the measurements that we're able to make in the solar wind. And that's what enabled a lot of I think some of the interesting physics we're able to do with wind. So, wind was launched in 1994. I started grad school at MIT in 1999, working with Al Lazarus, who was the lead of the Wind Faraday Cup instruments. So at that point, wind had been sampling the solar wind once every 92 seconds for about 5 years. And so we'd gotten to the point where if you just consider the Faraday cups, we'd made something like 3 million measurements of the solar wind. So every minute and a half, how much helium is there in the solar wind, how much hydrogen. The helium abundance, I'll talk about it more later, but it's about 5 to 10%. 5% during steady time is the maximum, 10% during a coronal mass ejection. By number density, it'll be helium in the solar wind. You can measure the temperature, you can measure the velocity, the density, those kinds of properties. So a lot of the time what we do is, the Wind spacecraft explored geospace since 2003. It's been parked at the first Lagrange point, which is a semi-stable point where the sun's gravity and the Earth's gravity basically cancel out, and the spacecraft can sit in this little halo. It's about 1% of the way towards the sun. We really like that location because you get to see the solar wind a couple hours before it reaches Earth. And wind operates as an upstream monitor. So a lot of great magnetospheric science that's done will take the wind data and propagate it to the magnetosphere so you have a sense of what the variation was in the solar wind, help interpret your magnetospheric or ionospheric data. Anyway, a lot of the time we'll take wind data and someone will just reach out to us and say, I want to know what was happening on July 14th of 2000 or October of 2003. Big coronal mass ejections, interesting solar wind streams passing by Earth. But I was sitting there as a graduate student trying to figure out, what can I do, as a novel new kind of science and with these data and a novel application. And what I realized was, we have these millions of data points and the solar wind varies, right? The speed changes, the density changes, the magnetic field changes. If you have enough measurements, you really get to explore a lot of different configurations. There's some fundamental numbers in a plasma. Plasma beta is an example of that, and I'll talk about that later. The ratio of thermal pressure to magnetic pressure. Well, it turns out on average at 1 AU, the solar wind has a plasma beta of around 1. The thermal pressure and the magnetic pressure are equally important. But sometimes the magnetic pressure is 100 times more important. Sometimes the particle thermal pressure is 100 times more important. So if you sample enough data, you can actually see how the solar wind responds dynamically and how it changes its behavior when plasma beta is different. And there are all sorts of other dimensionless numbers out there that we can, if we have enough data, we can see how the solar wind's behavior changes as those parameters change. And that's really interesting because there aren't a lot of situations on Earth where you can make the same kind of studies. We can only measure these distributions of particles in the plasma the way we do on a spacecraft like Wind in space. You can't do that in a laboratory. You'd have to come up with an instrument that was only a micron across, or it modifies the plasma when you stick it in. So all we have are numerical simulations or going up in space to observe these phenomena directly. So, okay, realizing the solar wind spans some very interesting dimensionless parameters. If you monitor the data long enough, figure let's move from an event to event analysis and try to do conditional statistics. So, does the dependence of X on Y agree with some kind of theory? How does Z change when you hold X as a function of Y? So let me give you some examples of that now. So on the right here, on the left, I'm showing some observations of what we call velocity distribution functions of ions or electrons in space. These were collected by the Helios mission, which until Solar Probe launched was the closest mission we ever had to the sun. And what we're looking at is each column from the left to the right is faster solar wind. So on the left, we're looking at pretty slow solar wind, a few hundred kilometers per second. All the way on the right, we're looking at pretty fast solar wind, 600-700 kilometers per second. That's about how much the speed of the wind varies at 1 astronomical unit, about a factor of 2 or 3, between 300 to 700 or 800 kilometers per second over most conditions. And then going from the top to the bottom, we're getting close to the sun. So at the top, we're at 1 astronomical unit. At the bottom, we're at about 1/3 of an astronomical unit at Helios's closest approach. And like I said, one of the cool things about studying space plasmas is we can actually make these maps. So a spacecraft sits there and it maps out the number of particles as a function of velocity as they're shown on these plots. And what would you expect to see? So if you think about the gas surrounding you in your room right now, gas at standard temperature and pressure, any one molecule in the air around you collides with another molecule maybe 1 million times a second. And so the air around you is in a set of collisional equilibrium. It's super collisionally coupled. If I were to superheat the gas right here, within microseconds, that extra heat would get dissipated. If I don't have a simple Maxwell-Boltzmann distribution that you get from simple thermodynamics, if at one point in space, what I mean by that is the particles don't have a nice simple bell curve distribution in velocity, then within microseconds, those little collisions will wash that out. So it's pretty easy to describe the dynamics of the air in the room around you because you don't need to worry about the details of which particle is moving at what speed. We can simply treat all the particles at any one point as having a total temperature or pressure, and that's close enough. That encapsulates and represents that bell curve distribution. When we go into space, this completely changes, and it's one of the biggest challenges in understanding the bizarre behavior of the solar corona and the solar wind. We don't have a lot of collisions. At 1 astronomical unit on average, a typical solar wind ion will travel, for maybe a day or two before it comes close enough to another ion to have a collision. And they don't ever actually physically collide. Just their electric fields are sufficient because they're charged that they gently deflect their directions. And so we talk about the solar wind as being a collisionless plasma, as very infrequent interactions between charged particles. And as a result, the velocity distribution functions can depart from the simple Maxwell-Boltzmann distribution. And the Helios data are a beautiful example of just how wild things are. If I look on the top, the slow wind near Earth, these color contours are the velocity distribution function. This is a nice, pretty simple Maxwell-Boltzmann distribution function, a little bell curve, same in every direction. For the slow wind, as I get closer to the sun, it seems about the same. Only at closest approach, this dashed line is the direction of the magnetic field, and there's some like extra particles moving along the magnetic field, escaping away from the sun. A slight departure of the solar wind ions from a simple Maxwell-Boltzmann distribution. That's the slow solar wind. What do we get if we look at the fast solar wind? If we look at the fast solar wind, we see even near the Earth, one of the craziest phenomena I've ever seen in a space plasma, what we call a temperature anisotropy. So if I focus on the core of the velocity distribution function of protons, the number of protons moving at different speeds around the spacecraft, I can fit a bell curve to this. I can extract a temperature. Just as a reminder, if you look at this equation on the bottom, I can relate temperature to a mean thermal speed or a spread of the number of particles in speed. Just one half the mass of the particles times that thermal speed squared is equal to Boltzmann's constant times its temperature. In normal thermodynamics, if someone tells you this is the temperature of the plasma, then you can just immediately take their mass and figure out, oh, okay, on average, they're zipping around at this effective thermal speed. What's wild about the solar wind, and we think the corona, is the plasma can have a different temperature if you look parallel to the magnetic field direction, which is again indicated by this dashed line, or perpendicular to the magnetic field direction. So same particles, but two different temperatures. If I look at the particle motion, like in this direction, if that was the magnetic field, they have one thermal distribution. They have one set of random motions. If I look the other direction, they have a completely different temperature. If you look at the fast wind closest to the sun, the difference in temperature can be like 3 to 1, 4 to 1. The particles are like 4 times hotter in their motion perpendicular to the magnetic field than parallel to the magnetic field. This is telling us something fascinating. What is it? Is it that something happened close to the sun and created this temperature anisotropy? Is something happening nearby that's creating this temperature anisotropy? Is the temperature anisotropy really large, but at some maximum value? What's limiting this temperature anisotropy? These are all questions people have about these non-thermal properties of the solar wind. So that gets me now to the first study that I did using large data sets. What I realized was there were theories out there that proposed that as the solar wind develops a temperature anisotropy, so the parallel and perpendicular temperatures are different, that can actually become unstable. So if T perpendicular is too much larger than T parallel, for instance, instabilities called the mirror or the cyclotron instability can kick in. And I'm not going to go into the details of the physics. But basically, the distribution becomes unstable. The plasma spontaneously starts generating waves. The waves scatter the particles around in velocity, and you wind up with a lower temperature anisotropy. If the parallel temperature is too much larger than the perpendicular temperature, then you get a thing called the fire hose instability. And that'll also serve to limit it. And people published different predictions for how quickly these instabilities would grow for given temperature anisotropy, for given properties of the plasma. But unfortunately, we can't build a spacecraft that travels with the solar wind. I can't go and take a spacecraft and somehow accelerate it to a few hundred kilometers per second and have it follow a parcel of solar wind plasma and see how an instability grows or changes, right? I sit there at one point and I watch all this data moving past us. Well, what I realized was, we could take predictions, for instance, that these instabilities become more important as that plasma beta number increases. And again, just a reminder, beta is the ratio of the thermal particle pressure, NKT, to the magnetic pressure, B squared, divided by 2 mu naught in SI units. So if this is 1, the pressure from the particles bouncing around is equal to the magnetic pressure. If beta is greater than 1, the particles do whatever they want. The magnetic field has to come along for the ride. If beta is much less than 1, then the magnetic field forces the particles to do what it wants. The solar corona, where you see beautiful loop structures in ultraviolet light, those loop structures survive because we think the beta is really small, so the magnetic field decides the dynamics. That's a low beta plasma. Well, there was a prediction that instabilities kick in and limit the anisotropy more rapidly as beta increases. So I go over here to the right to this plot, and I took 1.5 million spectra. This was my first paper I ever wrote for SolarWind 10. And I just histogrammed up the distribution from several years in the solar wind of the proton temperature anisotropy, T perp over T parallel. We did -1 in this version. So perpendicular divided by parallel temperature versus the proton parallel plasma beta, this beta, using T in the parallel direction. And this might not seem very exciting, but here's what we got really excited about. As you got to higher beta, as plasma beta went above 1 to 10 to 100, the observable range of proton temperature anisotropy got smaller and smaller. So that was our eureka moment. Like, oh, okay, can we look at a large data set of solar wind observations, not any one individual event, but take a large data set and piece together a story about the impact of these instabilities. And just a few years later, you could see how this technique began to be used to do really powerful differentiation between different theories for instabilities. So here's a paper in 2006. Now we're looking at several million more observations. The blue contours are just the raw distribution of the observations, again, as a function of T perpendicular divided by T parallel. So if it's 1 equal temperatures, and then this plasma beta. And what these contours are now is, instead of just saying, like I said in that first paper, when beta is larger, instabilities force the anisotropy to be smaller and smaller. Well, these are contours that say, how quickly would that instability grow if the plasma had that temperature anisotropy? And each curve has the instability growing an order of magnitude faster. So the idea is, if I somehow got into the plasma and I pushed it in this direction, every time I cross one of these lines, an instability turns on that grows more and more rapidly. And these are in units of the cyclotron frequency, cyclotron period, which is a couple seconds in the solar wind at 1 astronomical unit. So what I'm saying here is, at this contour, an instability would remove a temperature anisotropy this large in like 10 or 20 seconds. So in the scheme of the several days it takes the solar wind to get to 1 AU, we're gonna say that's fast. So on the left, these contours are predicted contours from what's called the cyclotron instability. On the right, these are the predicted contours from an instability called the mirror instability. On the bottom, when T parallel is greater than T perpendicular, this is a prediction for a mode called the parallel fire hose instability. To geek out a little, it's the fire hose instability if you force it to travel along the magnetic field. Here's a slightly more complicated version of the fire hose instability, where you allow the waves that are generated to travel at some oblique angle relative to the magnetic field. And look at what you can do. You can clearly see that the mirror instability and the oblique fire hose instability are a far better fit to the allowable range of temperature anisotropy in the solar wind than the cyclotron and the fire hose and parallel fire hose instability. So who cares, right? Let me just give you a couple examples of why this is cool. One, we're now able to say, okay, this theoretical bound does a really good job describing how the maximum anisotropy changes with plasma beta. So we can do MHD models of the plasma and the solar corona. And instead of trying to do a full 7-dimensional simulation of how these instabilities turn on and worrying about the individual particle motion in velocity space and physical space, we can just put in an equation of constraint. So we can basically remove 3 dimensions from a 6-dimensional velocity position simulation of the corona and capture the physics of these instabilities. So that's great because these are important to the acceleration and the heating of the solar wind. Another example, which I always thought was really cool, is you'll actually see simulations of material accreting into black holes where they need to know as the plasma compresses and fluctuates, how well it can do that and how large a temperature anisotropy it can sustain is directly related to how efficiently an accretion disk around a black hole or for an accretion disk around a young star that's forming new planets, how well that can lose angular momentum and have the plasma move around. And you'll actually see publications that take the Wind Spacecraft solar wind measurements of these instability effects and feed them into black hole accretion models, because this is the only place in the universe where we can directly measure this physics as it's happening. So that's pretty cool. Okay, so I could give like an hour-long talk on plasma microinstabilities. I'm not gonna do that. Let me just give another example of other large data set studies that people have done in a similar theme. So this is a cross-section, a theoretical cross-section of the electron velocity distribution. You can see, so this is the log of number of particles versus speed. And if it had a Maxwell-Boltzmann distribution, that bell curve, since this is the log of the number of particles, a bell curve turns into a parabola. This would just be the simple bell curve distribution that like the air molecules in the air around you have, their distribution versus speed. Electrons do all sorts of weird things in the corona and solar wind. There's a non-thermal kind of halo, we call it, extending in every direction around the thermal core. So basically a little tail of higher energy electrons in every direction. And then there's also a fascinating thing called a strahl. If you look in the direction of the magnetic field, electrons almost always have a slight excess of electrons moving along the magnetic field away from the sun. This is one of the ways that solar wind plasma carries heat away from the solar corona. Thermal energy in the electrons flowing out into the solar wind, being carried by this little strahl or extra bit of electrons. So if you think about it, how well a plasma is able to transport heat is kind of a big deal. If you're an astrophysicist and you're wondering how heat flows throughout a galaxy or a globular cluster or an accretion disk, if you're a solar physicist and you're trying to figure out how heat's flowing in the solar corona, if you're just trying to understand the energetics of the solar wind, it's really important to understand what this strahl is like and also what the maximum value of this strahl could be. So there's a simple theoretical value expression for the maximum energy we think electrons can carry as a heat flux. Here's an example of a study where on the x-axis, we're basically looking at an indicator of how collisionless the solar wind is. And there's a prediction that depending on how collisionless the solar wind is or collisional, there's a maximum limit to how much heat flux the solar wind can carry. The y-axis here is a measurement of how much energy is in the strahl relative to a theoretical maximum value, Q naught. And what you can see is fascinating in this study, that typical heat flux being carried by the solar wind increases in a very simple way as the solar wind becomes less and less collisional. And then there's this weird crossover where there seems to be a maximum value. So when the solar wind goes completely collisionless, electrons carry heat at a rate that's only about a third of the theoretical maximum. So big question that we're still trying to figure out, is this a universal? You know, is there a universal limit to how well electrons can carry heat in collisionless plasmas? And have we, by doing this large data set study, unlocked this really interesting universal process? All right, enough instabilities. Let me show you some cool things we've done with large data sets of, in this case, helium and the relative abundance of helium to hydrogen in the solar wind. And here what I'm going to do is I'm going to try to show you how we take a large data set and we tie it to variation in the sun. Here, let me skip to this one first. So this is a recent update by Ben Alterman, a former student of mine now at Southwest. And what he's looking at in this article is 23 years of data from the Wind spacecraft. So going all the way from launch to the end of 2018, how much helium is carried in the solar wind? This is a % ratio of alphas to protons or helium to hydrogen in the solar wind by number density. And the different color scales give you the speed of the solar wind. So blue is really slow solar wind. As you go up into orange and then green and then red and purple, you're going to higher and higher speed solar wind. And this black dashed line is the sunspot number. So you can see something fascinating, or I think it's fascinating. When there's a lot of solar activity, pretty much all solar wind has about 4 to 5% helium by number density. When you're in solar minima, the amount of helium escaping from the sun decreases. And for slow solar wind, it can drop by a factor of 3 or 4. So this has all sorts of interesting applications. One, it's telling us something really interesting about how variation in the surface of the sun, as indicated by the sunspot number, is somehow related to how plasma is emerging into the corona and how that plasma is being accelerated. Something's changing on the surface of the sun between low solar activity and high solar activity that changes how much helium is getting up into the corona and then changes how much of that helium is dragged out into the solar wind. So if we can understand connections between this variability and changes in the sun, maybe we can understand something about how changes in the corona impact the acceleration of the solar wind. If you're an astronomer and you're interested in how stars evolve, right? The sun and other stars lose helium as time goes on. If you're measuring if you knew the helium abundance in the core of a star, that's not necessarily going to be the helium abundance you're going to measure on the surface of that star. As the star loses helium, its surface properties are going to change. So if we can understand how the helium loss depends on the level of activity on that star's surface, the speed of the wind escaping, that'll impact how the helium abundance changes with time. And I'm just going to jump back now to a quick review now that you've seen that variation, just to give you some numbers. We know from the radius of the sun and how bright it is that in the core, by number density, about 10% of the core is helium. We know from helioseismology that within the convection zone, about 8% of the convection zone is helium by number density. So one of the things that I find mystifying is in the rare observations we have of helium in the solar corona, it looks like it's only 4.5%. And like I said, for typical solar wind, we never see it rise above 4.5%. In the solar wind, it varies between 0 and 5% for typical wind. In coronal mass ejections, it can go up to 10, 20, maybe even 30% by number density in rare regions within coronal mass ejections. So helium's interesting because it's one of the most variable parameters in the solar wind. And helium's also interesting because something just mysterious happens between the solar interior and the corona that basically halves the helium abundance. And figuring out what that filtering process is still a big open question. So I'm just going to give you some examples of some of the fun stuff we've unearthed by doing kind of large-scale statistical studies of the helium abundance. So on the left, what we did was this was from a paper I published in 2007. Lesson I learned from this is like maybe don't make massive, tall figures because then they're impossible to put in a PowerPoint presentation. So if you think you've got a really cool result, think about a way to display it that'll be easy for other people to put in their talks. Anyway, each of these rows is a different solar wind speed range, very narrow ranges. This is like 360 kilometer per second solar wind, 370, 380, 385, 390. And we're looking at the average helium abundance as a function of year, and we're looking across solar minimum. 1996, 1997 was a really deep solar minimum. And we saw the most mystifying thing. If let's pick a speed interval here, 385. This is the helium abundance. I've drawn in a sine wave to guide your eye, but hopefully you believe me. There's this 6-month periodic oscillation in the helium abundance. Now, if you're an experimentalist and you work on a spacecraft orbiting Earth, you hate discovering 6-month or 1-year anythings, right? Because what could possibly be happening at the sun that knows about Earth's orbital period? So spent a long time thinking that with this statistical analysis, we'd unearth some kind of calibration error with the instrument. But that's not actually the issue. What's happening is Earth's orbit around the sun is actually tilted by about 7¼ degrees relative to the rotational equatorial plane of the sun. So who cares about that? Well, here's a map in the center here of the magnetic field, the radial component of the magnetic field, a couple solar radii above the surface of the sun. This is from a theoretical model called a source surface model. It's driven by actual measurements of the magnetic field strength in the photosphere and then kind of extrapolated out of it. And what you can see during that solar minimum was this solid line with the little strikes. That's the neutral line. That's the heliosphere current sheet. It's where the polarity of the magnetic field reversed. In the northern hemisphere of the sun at this moment in time, you had inward magnetic polarity. On the other pole, you had outward magnetic polarity. And that neutral line where the polarity flipped was very nicely aligned with the equator of the sun. This gray region indicates the range over the course of a year that wind will move above and below the equator of the sun just due to that heliographic equatorial tilt. It'll move 7¼ degrees above the ecliptic plane, 7¼ degrees below it. And so it turns out what was happening was when the spacecraft, when the heliosphere current sheet of the sun was very well aligned with the equator, the spacecraft walked back and forth across this, and we saw this sine wave modulation of the helium abundance. Another way to look at that now that we've seen it is take all these data and just plot the helium abundance versus heliographic latitude. Now for the slowest wind, that was this blue stuff, there wasn't much of a trend. But for all the higher speed wind, you can see this kind of parabolic shape. So we learned something really interesting by doing this large data set study of the helium abundance. First, we see that the helium abundance cares about solar cycle. Then we see that the helium abundance cares about solar wind speed. And once we control for those and we look even more closely, we discover that at any one speed and a period in time, the helium abundance cares about the latitude of the spacecraft, or we think the latitudinal distance between the spacecraft and the heliosphere current sheet. So we're learning really interesting things about not only how helium escapes from the sun at different solar wind speeds and as a function of solar wind activity, but how that actually changes depending on how far away you are from the current sheet and presumably what different types of solar wind you're in. This is a snapshot of the same heliospheric current sheet model, but during solar maximum. And you can see now you don't have this nice simple excursion above and below the current sheet. And the signal goes away the moment the sun wakes up and that activity goes away. I'm just going to mention a couple other things we discovered here. Well, okay, let me show you one other thing. So this is removing that sinusoidal oscillation at solar minimum. This is the average helium abundance in the solar wind as a function of the speed of the solar wind. So it's this nice linear dependence, then it kind of flattens out. Below, again, we've got this big data set. This is a histogram of every measurement we've ever made of the speed of the solar wind. One of the things we found striking is fit aligned to this beautiful linear dependence, you can calculate a speed where you'd have no helium in the solar wind. Okay, and this is, the gray region is kind of 1 sigma uncertainty in what that speed is where there's no helium. Well, it turns out, look at this distribution of the observed speed of the solar wind. within 1 sigma of that speed where there's no helium, the solar wind occurrence rate drops by like 2 orders of magnitude. In fact, you know, in the like 20 years wind has been operating, there's like a handful of measurements of solar wind below here. Again, have we unearthed some kind of fascinating association between the acceleration of the solar wind fundamentally and how much helium comes along for the ride? You know, maybe there's some intimate connection back in the sun where there's a minimum speed of the solar wind. It's got to be above that threshold. That's this threshold, by the way. This isn't just like gravitational escape from the surface of the sun. I mean, it's much higher than that. But maybe we've identified some really mysterious connection between the helium abundance and
Justin, a couple minutes left.
Great, the acceleration of the wind. Okay, why don't I'm going to go real quick. I'm going to skip that fascinating thing there. Let me just say 2 things about Solar Probe and then 2 things about Sunrise. So Solar Probe is an awesome mission. Again, I could talk to you about it for hours. We start at 35 solar radii as closest approach. We'll end at 9.86 solar radii from the center of the sun. We're just looking these last couple weeks at our first encounter at 15 solar radii. Is fascinating. One of the points I just want to make with this group is, as opposed to wind taking data once every 92 seconds, our Faraday cup on Solar Probe takes data like twice a second usually. Given the way we're operating it, we're taking the equivalent of something like 366 years of wind data. And so you just can't like manually inspect all of that data. Here's just some plots of the data. I thought you might enjoy this. This is near our first perihelion encounter with the sun. And I won't go through the details of this. I'll just tell you one of our big initial discoveries was when we got close to the sun, it was just chock full of these violent structures where the solar wind speed jumps by hundreds of kilometers per second in just seconds. Magnetic field flips around, enabled by this high time resolution data. But we've got to figure out a way to actually analyze all that data. So Daniel Vetch just had a paper published on a cool machine learning algorithm that we use where, you know, here's a simulation where you have 3 populations in the data. You know, what you actually measure is this, right? People don't tell you how many populations are actually in there. And we use machine learning to actually take this image and it classifies it and tells us with incredibly good reliability if there are 1, 2, or 3 populations in there. And once it's done that identification, it unleashes an analysis code to extract the properties. You know, much better than, I mean, we'd never be able to sit there individually and do that. And we have examples of the reliability of it, how well it works. It's been really phenomenal. And I'll just end with the Sunrise radio interferometer. Like I said, I don't have any data here to show you, but the key points I wanted to make with Sunrise, if we wanted to actually send all the raw data from the spacecraft down, we're collecting radio emission from the sun at frequencies up to 20 megahertz. There's 6 spacecraft. We need to send petabytes of data a day down to the ground. But instead what we do is each spacecraft has a little GPS receiver on board, and they take a little snippet of data at the exact same instant in time, synchronized to nanoseconds. They take a little snippet of data 10 times a second. They process that data on board and they send the processed data down to the ground. And that reduces our data volume by nearly a factor of 10 to the 4. So doing a cool timing trick to reduce the data volume was really big for making this mission possible. You just can't afford to download petabytes of data from space yet. And then I think I already mentioned this, but another cool thing about Sunrise from a data point of view is we're actually moving almost all of our operations, like data pipeline for data processing for the Science Center into the cloud with a commercial provider for the first time, which will cut down costs, but also lets us scale the computations. That's pretty exciting. So I'm going to skip all this stuff. You can see I was very ambitious, and I'll end here with my just summary of what I discussed, and I'm really happy to take any questions if there's time.
Thanks so much, Justin. We already have actually several questions on Slido, so I will go ahead straight. So the first one is, can you please share your experience becoming a mission PI for those who might be interested in following a similar career path?
Yeah, sure. You know, I take everything with a grain of salt, right? Because I can't say that like you should emulate exactly what I did, because I felt like it was super random. But you know, I really liked building hardware, and I always felt that you know, that was something I wanted to do. And I don't think that, you know, please don't take this as saying like you've got to start doing it earlier in your career as you can. I met plenty of people that moved into doing hardware later in their career, but I dove into data and experimental stuff in college, and then I basically got shipped to MIT because they needed a grad student to help with Faraday Cup for the Discover mission. It was called Triana back then, but the NOAA Discover instrument was supposed to be my PhD thesis project, and then I was working on that, and then our postdoc who was leading it decided to go into the insurance industry and move to Europe, and it was great, and he's very happy, and that's wonderful. But we had like a year to deliver the hardware, and like there's no time to like hire another postdoc. So I basically got horrible grades in graduate school for a year, and took over the hardware responsibilities, got the instrument delivered to Goddard, which was great experience, right? You know, I was just, what do they say? Fake it till you make it. I mean, I had no idea what I was doing, but it was like, well, you know, we've just got to get it done. And then the mission was canceled. So fortunately, I was looking at the wind data to get practice. So I pivoted to doing science out of the wind data, and that was my thesis work. And then Solar Orbiter had a call for instruments, and I was like, there should be a Faraday Cup on Solar Orbiter. And my former PhD advisor was like, write a letter. And I was like, all right, fine. And I wrote a letter, and you know, it was like, oh, it was crazy. I mean, all these established people like reached out, like, you know, what are you doing? Like, we've got this whole plan. Like, okay, fine, we'll talk to you if that's what you want. And so even though I really didn't have a lot of resources other than I knew how to build that kind of instrument, I think that put people on notice that I wanted to build something. It didn't work out for Solar Orbiter, but then Solar Probe started looking like more and more reality. And I was making a ton of noise. I really wanted Solar Probe to have a sun-facing plasma instrument so we could continuously see the solar wind throughout the encounters. When we're really close to the sun, we're moving so fast, solar wind comes in like sideways, and you can sample it with a shadowed instrument. But we've got a really awesome Faraday Cup on there that can get up to like 1800 degrees Celsius, stare straight at the sun and measure the solar wind, and do it at a really high speed, because the flux of the solar wind is crazy. So it's a good signal. So a couple teams reached out to me. They were like, you know, would you be willing to provide this? I was like, yes. And then, you know, we're gaming things out, and it's like, can we really fit everything we want to put on the spacecraft? I don't know. If we try to propose everything, like it's going to look like maybe a disaster. Maybe we should break up into smaller teams. And I was like, I don't care. I just want to do this Faraday Cup. And then some people reached out to me, and they were like, we like your Faraday Cup idea. We think it would be more compelling if you could combine it with like some really simple, reliable instruments that have worked before. So NASA can go, okay, Faraday Cup is exciting. We should do it. We know we've got these reliable instruments. And they were like, but we don't want to deal with the horrible stress and baloney of being a PI. So do you want to be the PI? And I was like, sure. And I went back to my boss, Leon Golub, at the Smithsonian like a couple days later. And I was like, he thought I was going to go to ship, you know, an idea of providing a piece of hardware. I was like, well, I'm a sweet PI now, maybe. And then just, you know, did a ton of learning, getting the team together, worked with a lot of really skilled systems engineers and project managers who helped me and gave me a ton of advice. I wish there'd been a NASA intro to being a PI thing when I was doing it, because I was super envious when they started offering that, because I had so many interactions where I think NASA or the leads of the missions thought I was being crazy when I just didn't know how you have conversations about things like that. So anyway, that was kind of how I got to Solar Probe. And then Sunrise, JPL reached out and they were like, we want to do small sats in radio. Do you have any ideas? I was like, yeah, this. And we were like, yeah, let's work together. So once you build up the expertise, it gets a lot easier with time. It can get stressful though. Make sure to take time out for your mental health and physical health. I'll just say that.
Definitely. I go quickly to a super quick one since you mentioned Parker Solar Probe. Do you know which parameters, like what was the reason why the closest approach value of 9 solar radii, I think, like what went into deciding that?
Yeah, okay. So we want to get below the Alfane point. So, we think that, so 2 key distances, the solar wind will go supersonic at one point. It would be awesome to cross the supersonic point, but that's like maybe a couple solar radii, like, Solar Probe plus can figure out how to survive at those distances. The next out critical point is the Alfane point. So I was talking about plasma beta. When you're below the Alfane point, that means the solar wind flow speed is less than the Alfane speed, which is kind of the upper speed limit of the solar wind. When we're below that, we're in plasma that's like magnetically communicating with the surface of the sun. So we think of that as like, if we can get below the Alfane point, we are in the sun's extended atmosphere from a plasma physicist point of view. So that's what the below 10 RS is driven to, like hoping that we get below it, and we're going to get below it.
Thank you. And then I try to combine 2 questions about machine learning. So the first was, how do you tell a success story from the use of machine learning for science, and what are the narratives that can inspire change? And the other one is, can you say more about how your machine learning would facilitate similar discoveries to the one that you showed in the initial example? So scientist intuition to discover patterns.
Yeah. Okay, let me try to give a coherent response to that. So wait, what was the first part of the question? It was like, what are other science examples of the use of machine learning?
So what narratives can inspire change? Yeah, sorry, I tried to combine the machine learning questions into one, okay, because there are so many on Slido.
So let me tell you, like, plasma instruments are a pain in the neck. There's so much interpretation of those velocity distribution functions to make sense of it, right? Sometimes the solar wind will split into like the protons will look like 2 separate Maxwellian populations. They have different temperature anisotropies. There's a heat flux. If depending on the instrument you're using, different ion species show up on the same thing. So a lot of composition instruments that measure like charge state and energy per charge, there might be like 30 different species in there. And people are like, how much carbon-4 is there in the solar wind? And it's like, okay, let me look at a map with 30 bumps in it and try to figure out which one's the carbon-4, whether or not I can see it or not. We're still at a point where a lot of the analysis is done manually, or a scientist says the peaks have to appear here or here, so do this and hardwire it in and fit it, and then have some metric to tell me if it's gone completely exploded, and that's about as good as we do. And so our analysis of like the Faraday Cup data is like 1 million lines of code with 25 years of like, and then this person noticed that when it fails this way, that happens. So if that happens, try doing this. No, that was wrong. Then this person realized, try this instead. So I think in the composition instruments, the solar wind instruments, mass spectroscopy, there's so many realms and plasma instruments where you're trying to find a bunch of bumps in noisy data and figure out which bump is what. So find the bumps, categorize the bumps, and then you can go off and do a detailed analysis, but also know when the finding of the bumps has gone wrong. And, I can't look at, 500 million maps of bumps in my lifetime. So we need accelerated processes like the machine learning.
Thank you very much, Justin. I think we have to move on, but someone has copied the other questions over to Slack, so you can maybe go there and try to reply there. Thank you very much. And now I pass to Daniel.
I will find the Slack. All right, take care.
Great, thank you, Justin, and thanks, Erica. So I'm just stepping in quickly here for Lika, who has to be away for a short period. And it's my pleasure to introduce Dr. Angeline Burrell, who is a research physicist in the Space Science Division at the U.S. Naval Research Lab. She received her bachelor's from Smith College, a master's from Dartmouth, and a PhD from the University of Texas at Dallas. Her main research interests are in ionospheric interaction, including ionosphere-thermosphere coupling and the connections between high and low latitude processes. Much of her investigation is focused on long-term ionospheric variability. So sorry about that. My screen just got covered up here. Much of her investigation is focused on long-term ionospheric variability, looking into sources behind seasonal and solar cycle variations in the quiescent ionosphere. Dr. Burrell is an observationalist at heart, and she has spent time improving the quality and quantifying the error in various data sets, including such things as SuperDarn and Cindy, and she also uses the SAMI3 NEMO model. She's active in the Cedar Python community and playing a role in community organization, education, and package environment. So with that, I'd very much happy to turn it over to Angeline to present her talk today.
Thanks, Dan. Hi, everyone. Today I'm going to be talking to you about space physics data with the goal of assisting your development of studies that apply big data methods to this field. Next slide. I'll start by going over some of the different data that's available by region and type. Then I'll present some of the challenges to using big data techniques in space physics and examples of some applications of these techniques. Finally, I'll provide some reminders of things to consider when you start your own study. Next slide. So, space physics, for those of you who aren't familiar, encompasses the area of space that reaches from about 100 kilometers above the surface of the Earth, or the equivalent boundary at another planet, to the outer limits of the solar system, though it does impact and may arguably include exoplanets. This includes a wide variety of different disciplines and subfields, as we've already seen today, including solar physics, interplanetary studies of the solar wind, Earth-centric studies of the magnetosphere, ionosphere, and neutral atmosphere, as well as similar studies of other planets. Each of these fields may be, to some extent, pursued independently from the others. However, there are ways in which they overlap. For example, studies of Earth magnetosphere frequently use solar, interplanetary, and ionospheric data to inform their treatment of the magnetospheric state and boundaries. Another example is the field of comparative aeronomy, which improves our understanding of upper atmospheres and ionospheres in general by comparing observations from different planets and figuring out how the conditions at each planet affect the differences in the observations. Yet another way these different regions are tied together is through the types of measurements that are made to study them. Next slide. Space physics data measurements may be made either in situ, which means observing a quantity at the place where the thing is, or remotely. I've listed several types of instruments here based on these two measurement styles. Note that instruments from each group may be used either in a ground or space-based capacity. Each platform presents its own strengths and limitations. Several of these instruments measure the same quantities through different methods. When and where we use them depends largely on practicalities such as platform, temperature requirements, and power requirements. As an example, setting up a ground-based observatory in Mars' southern hemisphere would be great because we've got crustal fields present that we'd like to know about, making it an area of great interest. But it's also very difficult because it's much colder than the northern hemisphere and receives less sunlight, making it harder to power whatever you put down there. The surface is also higher, making it landing operations more difficult. Another example that demonstrates flexibility is shown in the two figures on the right. The top figure shows the EPOP instrument suite, which includes the 4 antennas extended outwards from the red square on the front. These are the antenna for RRI, the radio receiver instrument, which is a high frequency signal receiver. On the bottom is the super darn Cyclovir radar, whose main array of 16 antennae in the front of the image both send and receive HF signals. Both of these instruments fall under the remote sensing radar category and measure similar regions of the ionosphere, but have different platforms and operating capabilities. Next slide. The quantities that these various instruments measure may be broadly grouped into 4 types: neutral gas properties, plasma properties, electrodynamic measurements, and radiation. The figure on the right shows a part of the current NASA fleet dedicated to space physics studies. Each of these missions carry enough instruments to independently answer important science questions about at least one part of the space physics environment. Many of them carry similar instrumentation, creating an extended spatial and temporal coverage of a particular quantity. This is very important for space physics studies because, as we've seen already, a lot of variability is driven by very long-term processes, such as solar variability and planetary tectonics. When taking an observational approach to a science question, it can be tempting to use the instruments that you know already, or other missions with similar instrumentation. It can be helpful to take a step back and consider the physical properties you want to work with and extend your data search based on these categories. Next slide. Now that we're broadly familiar with different data types, what challenges to these the challenges that these different data sets present when we're looking at them from a big data perspective. The first challenge is data access. Observations may be difficult to obtain due to technological limitations, such as satellite downlink availability, operational modes, especially when they're designed to protect instrumentation during interesting space weather events, and the lack of connectivity at remote locations, such as Antarctica. Other limitations are more programmatic. A satellite may not take observations for a period of time, even though it's capable of doing so due to funding priorities. There may also be a lack of funding for data processing, analysis, and hosting services. The second challenge is data complexity. Many data sets were conceived to answer a particular question and are well designed to do so. That doesn't limit their usefulness to only answer that question. The design may not be optimized to do what you want. One example of this is satellite constellations. 2 common designs are a string of pearls, where satellites follow one after the other, and a maximal coverage, where the satellites are separated to provide the most comprehensive coverage of a region or planet possible. The first option provides high temporal resolution at the same location, allowing you to easily study small-scale variations. However, the string of pearls design isn't great if you want to examine something like the planetary response to an event. It doesn't mean you can't use observations from a string of pearls constellation or even a single satellite to answer larger scale studies. It just means you have to be more careful when setting up your methodology. The third challenge is data size. Some of this you can throw money at and buy better computational resources or pay people to make your analysis code more efficient. Some of this is not really in most of our control. When moving beyond case studies, we need not only a lot of data, but a lot of data of the correct thing at the correct place. And since our area of interest is very large, this is hard to do. Let's move on to some ways we can address these challenges on the next slide. Starting with data access, many data sets are available through a variety of online portals. All of the data I'm showing here is considered publicly available, but many of the sites require registration or have limitations on data usage, so make sure that when you go there, you read their rules of the road. Next slide. Most, but not all of these databases allow scripted data access or have software packages that supply download scripts. I've lightened the text on the sites that don't allow simple scripted access through a portal that is either open or has an online registration form. Scripted data access is essential in large data studies, unless you have a student who's willing to manually click on a web page for several months. Many of the accessible portals also have software packages that improve data access and may even simplify data processing. I've included the ones I know about on the right. Most of these are in Python because that's what I use. But SpeedS and the SuperMake API are in IDL, and Madrigal Web has both IDL and Python implementations. Next slide. Another challenge to accessing data is obtaining it at the desired quality level. A lot of satellite data follows the NASA guidelines outlined in the yellow table on the right. This broadly separates science quality data from instrumental measurements at level 2. Level 2 data and above requires less particular knowledge of instrumental operations and contains the geophysical measurements you actually want for most studies. And although the data at this level is considered clean, the L2 and above data sets may not have the optimal processing for all possible conditions. Because of this, it's very important to read the data documentation and validation papers. It's also customary to contact the PI. In my experience, both as a student and later in my career, PIs are happy to talk with you about the best ways to use their data in your particular study. Sometimes this can even lead to secondary projects and collaborations. There are also software packages that include routines to process or clean particular data sets to a higher level. For example, PySat NASA not only downloads many data sets from CEDAWeb, it also includes cleaning routines developed for CNOFs, ICON, and GOLD data sets. This cleaning correctly applies the L2 data flags as described in the data documentation, and in the case of the Cindy IBM dataset, applies further cleaning routines developed during the initial instrument analysis phase and is published in journal articles. Another example is the Ssj Auroral Boundary code, which takes the DMSP Ssj electron precipitation data, downloads it, and determines the auroral boundaries. Now that it's becoming common practice to DOI analysis code, more and more software packages such as these are available. Many of these packages may be found under the projects page at heliopython.org. All right, next slide. Of course, not all data sets use the NASA satellite levels to indicate how clean or how processed their data is. Ground-based data, for example, rarely uses these levels to define their data outputs. That doesn't mean you can't map them this way, though. I've shown as an example total electron content, or TEC, from the Global Navigation Satellite System. The top two images show level 1B data, which would be obtained from the CEDAS repository. This data isn't science level yet. The carrier phase on the left needs to be combined with the pseudo range on the right to obtain a TEC that has both the small scale variations provided by the carrier phase and the correct absolute magnitude provided by the pseudo range. You also still need to account for the angle between the receiver and the GPS satellite, as well as the satellite and receiver instrumental biases. Once all of this is done, you get the level 2 data shown in the circles on the bottom left. The background of this figure is a climatological model, and the color of the circle boundary indicates which measurements are considered normal, those with black outlines, or abnormal, those with red or white outlines. You can see, for example, the bright green point with the white outline along the west coast of Canada. It has a much larger magnitude than the surrounding data points and what is expected from climatology. This could mean that something interesting is going on physically, or it could mean that your receiver bias is bad. The final figure on the bottom right shows the gridded median TC from the MIT Haystack Madrigal database for the same time as the level 2 figure. This level 4 data uses information from multiple measurements to provide higher confidence in the vertical TEC results. Keeping these different levels in mind can help you figure out how cautious you need to be when designing your study and methodology. Next slide. The next challenge I'll go into more detail about spans the data access and data complexity categories. This issue is instrumental calibration, which was mentioned in the first talk. As I mentioned before, many of the same types of instruments are deployed on different platforms in different locations. Each instrument has its own particular set of biases that need to be calibrated. Some of this can be done in a laboratory, but things change once operations begin, and time may also cause variations in instrumental bias due to things like extreme temperature changes or even damage to a portion of the instrument. You also may not have a correct value to which an instrument may be calibrated. This can make it difficult to combine data from different platforms, especially if they don't overlap in space and time. An example of this is the different IVM, or ion velocity meters, that have flown on board a variety of different low Earth orbiting satellites. It would be wonderful to just combine the outputs of all these instruments, but there are very few conjunctions, and so when designing a study that uses each of these, you need to treat each data set with care. Other data sets have been cross-calibrated and have science outputs adjusted accordingly. An example of one of these wonderful data sets is presented in the figure on the right, which shows magnetic field perturbations in the northern hemisphere. The green dots and lines show the cross-calibrated individual measurements, and the black dots and lines show the mapped results. Each output makes for a simpler study than combining observations from different IBM instruments, because the SuperMag results have performed the cross-calibration needed to easily combine the results from different instruments. Next slide. Data size is a particular challenge. The typical problem, assuming you have a lot of data, is that you don't have a lot of data where you want it. The example I'm using here is from a recent comparative aeronomy study that I did, which compared the TEC at Mars and Earth. At Mars, we had enough data to study the seasonal and solar cycle variations in 3 different regions at dawn and dusk. At Earth, we had a lot more data, especially if we were just limiting ourselves to the same types of times and places that we had at Mars. As you can see in the figure on the right, coverage is still less than ideal. You'll notice in each of the little black boxes, we have coverage where we have islands or land masses, and then not a lot over the ocean. However, you have to work with what you have. Even with these gaps where we wanted to have data, we still had so much data that with decent computational resources, it took over a year to download and process. Anyway, as you can see in the figure, so anyway, an additional challenge in this study was finding a processing method that worked equally well on the large Earth data set and the smaller Mars data set. We ended up settling on using the Huber method for linear fits, which is illustrated on the left. This is an excellent, robust method of linear fitting that identifies outliers and uses the inliers to find the linear regression. This ended up working well for both data sets because it didn't allow the heavy skew in the Earth data to influence the results. And it also worked well for Mars, which had a lot more variability at lower solar zenith angles where the instrument was just starting to be useful. All right, next slide. Combining complementary data types is another way of getting around the not enough part of the data size problem. Some observations are just harder to make than others. A completely unrelated example would be dark matter, which you can't measure directly, but you can measure indirectly. In space physics, you frequently need to indirectly measure portions of the space environment, either because it's hard to make measurements there, or we haven't successfully developed an instrument to measure the thing that we want, or the data just isn't available when and where you need it. I'm showing another one of my old studies as an example of this. For this study, I wanted I wanted to determine how plasma transport across the magnetic equator changed as a function of altitude and season during solar minimum in the topside ionosphere. The equation on the bottom describes how this typically works. Unfortunately, we don't have measurements of the neutral wind at the desired altitudes, or the ion-neutral collision frequency, or the electron temperature. This means we can't fully measure any one term of this equation, except for the field-aligned plasma drift or flux. However, we can use distributed measurements of the ion density and the height of the peak ion density to infer the behavior of the neutral wind at the height of the ion density peak and its impact on the interhemispheric plasma transport. Alongside other measurements, such as the E-cross B drift, we had enough data to qualitatively answer the question posed. Next slide. So now I'm going to move past these challenges to performing big data analysis techniques studies in space physics and show you 2 examples of studies that use one of these techniques. Next. This technique is data interpolating empirical orthogonal functions, or Dyneios. Empirical orthogonal functions are a classic method of describing the variations in a large data set. Dyneios uses singular value decomposition to find the best combination of empirical orthogonal functions to describe a data set. It was developed in the atmospheric community by Vickers and Rickson, and iteratively settles on the best combinations of EOFs needed to estimate data in regions where none is provided. The figure on the right is from their paper and demonstrates how it performs reconstructing a truth data set created from synthetic data using input with partial coverage. Next slide. The first example study was performed by Rob Shore at BASS. He wanted to characterize the external and induced magnetic field, or EIMF, at polar latitudes where it's most variable. He chose the Dyneios method because the EIMF is characterized by high spatial and temporal variations, making it a good candidate for being appropriately represented by empirical orthogonal functions, and because the data coverage as a function of the quasi-dipole magnetic latitude and magnetic local time varies a lot and is never complete. When designing this study, he first started small, selecting only the northern high latitudes in February of 2001. Rob then consulted the data validation papers and removed the annual magnetic variations from the supermag data to retrieve the higher order variations that make up the EIMF. Then he considered how the distribution of the data would affect the Dyneios technique. Because clusters of data near the instruments would bias the results, he binned the data as shown in the figure on the top right. He also decreased the time resolution from 1 minute to 5 minutes to address processing costs. At this point, he could process the data, which involved removing the mean of the entire time series from each bin and applying the Dyneios method. This yielded a number of modes that could be examined to determine how well they describe the ongoing physical processes. As shown in the figure on the bottom, the first 6 mode describes 65% of the variance in the EIMF over the month in question. Next slide. The variation from the mean magnetic field perturbations for February 2001 are shown for each of these 6 modes in the figure on the right. Note that although the upper and lower limits for each color bar are different, red is always positive, blue is always negative, and 0 is always white. Because Dyneios is automated, there is no guarantee that the EOFs will describe a physical process. However, when Shore examined the first 6 modes, they did appear to be related to known polar equivalent current systems. The most dominant mode looks a lot like the DP2. It shows a 2-cell convection pattern with strong east and westward equivalent currents that are at their peak in the morning and afternoon. The second mode appears to capture DP1, or the substorm wedge. The next 4 modes can be used to alter the spatial extent of these 2 equivalent current types. Since Dyneios provided useful physical insight to the month of data, it now made sense to extend the study. Next slide. Now considering 12 years of data in the Northern Hemisphere, the EOF output was not as simple to analyze. Because of this, he applied graph theory to the EOFs, identifying quantitatively similar patterns. These were then combined and examined to determine their role in describing the EIMF. As before, the DP2 and DP1 emerged, but now the DPY, or the equivalent current associated with IMF-BY, and the NBZ, the equivalent current associated with northward IMF-BZ, also emerged. This encompasses pretty much any orientation of the IMF, since the DP2 describes the influence of the more common southward IMF-BZ. Shore then compared the long-term variations to the equivalent current system patterns. An example of the seasonal variations are shown on the top row, and an example of the solar cycle variations are shown on the bottom row. Thus, Shore is able to provide an independent measure of solar terrestrial coupling using a solar cycle's worth of supermag data and 2 big data techniques for analysis. Next slide. In our next example, Russell Stonebach from UTD uses Dyneios to improve the spatiotemporal description of the meridional E-cross-B drift. The figure on the left shows the E-cross-B drifts from the CNOF SINDI IBM instrument. This data has been down selected to include only high quality data. As you can see, there are regular gaps where the elliptical orbit that CNOS had reaches higher altitudes where the O+ density is too low for the instrument to work reliably. When the satellite orbit processes to cover all locations and local times over about a 3-month period, there are some times and places where coverage is just never very good. This means that if you simply apply Dyneios to the E-cross-B drifts, it's poorly constrained in some areas and the output isn't physical. You can see this in the red line in the figure on the top right, where strong upward E-cross-B drifts are seen pre-dawn and into the early morning for a very short period of time. Stonebach addresses this issue by introducing potentially complementary data sets. In the middle panel, the NMF2, HMF2, and F2 peak thickness for the area in question are used along with the meridional E-cross-B drifts to constrain the potential empirical orthogonal function fits. This does a good job and results in an E-cross-B drift that are upward and downward at the times and places where this is expected, but still maintains the daily variability present in the observations. The bottom panel shows the results of combining the SINDI E-cross-B drifts with the F10.7 and DST. This does a bad job and highlights that you need to be careful when combining different data sets so that you don't overly weight quantities that are important, but not directly tied to the physical processes of interest. In this example, while the F2 peak characteristics don't drive the E-cross-B drift, processes such as lower atmospheric tides that cause day-to-day variability in both the F2 peak and the E-cross-B drift are better captured when both are used together. All right, next slide. From these examples, we can draw the following recommendations to keep in mind when designing your own study, be it in space physics or a completely different field. These are, number 1, start small. Make sure things work before you invest a lot of time and resources. Number 2, read the instrument and calibration papers. You can save yourself a lot of heartache and reduce unnecessary tangents by not trying to explain an instrumental effect using physical processes. Number 3 is contact the PIs and analysis experts. They're usually friendly and happy to be involved in a well-designed study. Number 4 is test your analysis on a sample data set. This is technically also point 1, but it bears repeating. It's basically a unit test for science. Make sure your analysis method does what you think it does. Number 5, explore different methods and data sets. Sometimes we get tunnel vision and end up trying to use a hammer on a screw when the screwdriver is lying one office over with your colleague. hopefully we're all adding tools to our toolbox at this conference. And finally, validate your results. In space physics, it's unfortunately common to exclude both error bars and validations for new types of data sets and techniques, and we should just be better. Next slide. I'd like to acknowledge the people that made the Madrigal TEC and SuperMag data products that I showed in this presentation possible, as well as CNR for supporting me. And now I'm happy to answer any questions if we have time for that.
Yes, we have a good amount of time for questions. So I think I'll just turn it over to Erica, who's on Slido and has a number of questions lined up. Thanks for a great talk.
Thank you indeed, Angeline. I will go ahead with the first question. We have some on slide already. Are there any Python libraries used for thermospheric or ionospheric models, such as okay, I will just read the entire
IGCM?
Yes, thermospheric, ionospheric, electrodynamics, general circulation model. Yes.
So yes, but so one project I'm working on is PySat models, which I am developing primarily to support my efforts in model validation. And one of the things it does is has a methods for reading in TiGCM data, and that it reads it into an X-array structure, which is then easy to use for any sort of typical Python analysis. Because it uses the PySat infrastructure, it's also easy to incorporate observational data sets along with side your model results, but of course it's not necessary to do so. I don't know of any Python code that runs TiGCM, but I wouldn't be surprised if something was under development. I know Liam Kilcommons works a lot with some of the groups there, and he's developed Python interfaces for some of the codes there. For the life of me, I can't remember them off the top of my head right now. So I don't know of anything that does exactly what you want, which would be to run TiGCM through Python. But I wouldn't be surprised if something like that came along in the future. And if you have the output, then I would love it if you went and beta tested PySat models.
I'm sure that there must be something in the works, because Python is such a big community with people like working on so many different libraries. Thank you, and let's go to the next question. Much of our creation of mission data archives seems to occur post-hoc. How can we build better data management earlier into the mission design instead?
Right. So as someone who has always come on late to mission teams, I would say reaching out to your potential user base at the beginning of mission design would be the best way to do it. I know that there is a lot to do, and the last thing you're really thinking of is, how is someone who is not familiar with this instrument going to start using it externally? But it would really help. Fortunately, we have a few of the databases that, like CETA-Web, that where you know all of the NASA instruments are going to go to, and there are ways of getting it. But even there, not all of the data sets are completely standardized. But I think just a lot more asking and listening to new users in the community would be really helpful.
For sure. I had problems unmuting for a second. Okay, let's go to the next question. Are DOIs the best way to recognize the efforts of data providers because they're typically not counted in the same way as citations, which are used in funding decisions or career advancement? Do we need other avenues instead?
So the two avenues that are traditionally used are, of course, offering authorship to people who provide data to you in your studies. And that is one way of doing it. I like DOIs because they make data sets more countable, and because you can have versions, you can revise your data set, but still go back and replicate old results and ensure that things haven't changed or have changed in a better way with the new data set. What we really need, of course, is a change in the culture of our field, where we value contributions from people at all stages and at all parts, acknowledging that data analysis and data cleaning is a foundation of science, and you can't do anything without it, and deserves to be recognized and counted. If you don't change the way you evaluate people and you just try to hack metrics, then you're not really going to have the change that you need. So we need to make sure that we cite data, that we talk about the type of analysis that was done on our data, instead of just saying, oh, I used DMSP data. Cite the instrument paper, cite the data set paper, talk about the types of cleaning that you did on the data. It's important to do this. I think these kind of things will help us move towards the direction of acknowledging that these foundational parts of science are important and deserve to be valued.
And lately, I think it's a thing that started like a couple years ago in the UpJ journals. Now they have under the, like at the end of the paper, now they have the section where you can write facilities, which are like spacecraft instruments that you use, and then software. So it's good to cite in there the instrument, like if you don't want to do it in text, at least in there, instrument papers and software papers.
Absolutely. And another thing that a lot of our journal articles are introducing now is the role that different authors play in a paper. Mm-hmm. And there, if someone is just included because they did the data analysis, you would be able to say that. And that way you can distinguish the people who contributed to the theory and discussion and the people who contributed to the foundation of the theory and discussion, the data.
Definitely. Next one. So we had so many missions in the last few decades, and the number of missions is increasing, which means that the number of instruments is and types of instruments are increasing. So what efforts do we need to make to make sure that we are going to have cross-calibrated data over the long term?
I think, well, funding people to do the studies, that's number one. And number two is not allowing gaps. So one example is CNOFs and ICON, where ICON could be perceived as the follow-on from CNOFs, who could be perceived as a follow-on from ROCSAT. But there's no overlap between these instruments. So even though they carry a lot of the same instrumentation in the same region, we can never cross-calibrate them. We can only perhaps do so in combination with an instrument that continues to work over the long period of time, which in this case would be the Hikamarka ISR. But the biggest barrier, I believe, really is the funding. Programmatically, institutions like NSF, NASA, STFC need to acknowledge that this is important. It's not just important to put a new thing out, it's important to make sure that you can use the new thing alongside old things. Some instruments do this well. JSON and Topex is an example of this, but it's not as common in other areas.
Yep, and so this other question starts with appreciation for your point about testing with sample data sets. And should this be something with request from all data providers? And how do we format those data sets?
Oh, I would love that. I would especially love this from modelers. It would be really great if you just included a sample file output for a particular day. It doesn't even have to be the same day across all of them, just so that, you know, can make sure that things are working correctly when I try to compile it locally. And not just like the little tests. For observational data users, I think it would be valuable to have a sort of step-by-step with images example of a simple analysis. Some of this is already done. It's just harder to find. It's in the early papers, the validation papers. And unfortunately, most instrument teams aren't as good as one would hope at archiving the results or the publications of everything. Which is fair, especially for a lot of the older missions, because like there's no one around anymore to maintain the web pages. But then we lose all that work and effort that someone did to try to make sure that you could easily use the data set. I don't really know an answer to this one, apart from perhaps the places that archive the data also housing a place for these papers. One of the things that we're doing in PySat is trying to include the acknowledgements and the references for each data set, so that when someone starts using a data set, they know where to go look to read about it and figure out how to use things. So if you are writing an analysis code package for your software, if you include the references that point people to places to go read and examples to follow, that would be brilliant.
Yes, it would make stuff easier for everyone. And I have a last question on Slido, which there was a last question. Oh, okay, it was upvoted, so it went up. Do you think that we need some dedicated, and I know that the answer will be yes. Do you think we need some dedicated global community working towards integrating all the data in one place? And obviously we will need funding, I guess.
Oh, I mean, I would love that. It's never going to happen. I mean, even if we just had a global website that had links to everywhere, that would be enough for me right now. Having worked with SuperDarn and knowing how hard it is to get data in a particular format from a government that has bad political relationships with a government that's already a part of the project, I'm not hopeful. But if we can have individuals from all over the world contribute knowledge of their databases, that would be a start. And I think that's something that we could do.
Definitely. Thank you so much, Angeline, for this great talk and the great Q&A. And now I pass the word to Daniel.
Thanks very much for that. That's great. So I'd like to introduce the next speaker. Is Fernando Perez. He's an associate professor in statistics at UC Berkeley and a scientist at the LBNL. I guess that's Lawrence Berkeley National Lab. He builds open source tools for humans to use computers as companions in thinking and collaboration, mostly in the scientific Python ecosystem, IPython, Jupyter, and Friends. His research interests include questions at the nexus of software and geoscience, seeking to build the computational and data ecosystems to tackle problems like climate change, with collaborative, open, reproducible, and extensible scientific practices. He is co-founder of the 2i2c.org initiative, the Berkeley Institute for Data Science, and the NumFocus Foundation. He is a recipient of the 2017 ACM Software System Award and the 2012 FSF Award in the Advancement of Free Software. So with that, I'm very pleased to introduce Fernando and looking forward to your talk.
Thank you, Daniel. I appreciate the introduction, and thank you to the organizers for the invitation. Quick check, is my audio clear enough?
Yes, your audio is fine. Are you sharing your screen yet?
Yes, and so I want to thank Dr. Burrell for a wonderful presentation and a number. Let me switch to my slides. So I want to thank Dr. Burrell for a wonderful presentation, which actually opened up on a number of topics that I hope to dive a little bit deeper. So I think we are all concerned with the sustainability and the funding and the structures that will enable a future of open science where we take advantage of all of the kind of wonderful opportunities that the cloud offers. And I'd like to spend a little bit of time thinking about these topics. So today, open source software tools have had pervasive impact across the sciences. Just to put up a few highlights that have been meaningful to me, these are by no means the only ones. There is definitely an extremely biased selection of tools and projects that I'm in some manner connected to. But I suspect many of you saw a few years ago the big announcements about the first observational experimental data of the evidence of gravitational wave propagation. This was an event that made a lot of noise in the scientific community and also in the broader public. The image on the left is the first figure on a paper, on a physical review letters paper that I'm sure some of you have seen, that will probably be one of the most cited papers in physics for years to come. And this was extremely meaningful to me because every figure in that, every subfigure in there was made with NumPy, with SciPy, with Matplotlib, with tools that I became connected to back when I was a grad student actually in Colorado in physics at CU Boulder. And we began building these open source tools pretty much against the advice of everybody in the field who said, no, this is ridiculous. We have MATLAB and IDL already. Go back to writing math and physics papers. And many of us thought it was important to have open tools for science that would enable something like what's on the right, which is that the LIGO collaboration publishes Jupyter notebooks that include all the code for the analysis, and that anyone clicking on one web link can actually access and listen to the data of two black holes merging into one another 1.3 billion light years away, with fully open tools that any child anywhere in the world can access with as long as they have internet access. So we have had pervasive impact, and today it's become routine. A couple of years ago at Berkeley, we had the opportunity of seeing the team that led the Event Horizon Telescope imaging of black holes make their first public presentations. By coincidence, they were both at UC Berkeley that week. Shep Doleman, the head of the collaboration, and Professor Katie Bauman from Caltech, who headed the imaging group. And they presented a bunch of Matplotlib figures, again, where they discussed the analysis that they did to form this first spectacular direct image of a black hole. A few months ago, Katie Bauman was speaking at an event at EPFL, where I also had a chance to speak. And I was delighted to see this slide that she put up. After talking obviously about her work, she put up this slide where she had this rapid summary of all of the pieces of open source software that fed into the analysis tool chain that they presented and that the Event Horizon Telescope collaboration used. This kind of analysis was actually done by GitHub. I think the reason why somehow Daniel's video may be split, maybe still pinned. At least I have it on mine. On my window, I'm still seeing Daniel's logo on his screen. It is. I think it's because Daniel's is pinned. I don't know if it's possible for Daniel to unpin it so that my video occupies the whole window. Daniel Marsh's video is pinned.
Yeah,
I don't have the ability.
I can't control that, unfortunately. So hopefully Brian can unpin me.
Okay. I think, folks, I was able to. Nope, I was not able to get rid of it by hiding video. Okay, sorry folks about that little audio video confusion that we had on the presenter side. Apologies for that. And so continuing, when Katie Bauman presented this was actually an analysis done by a team at GitHub, and they've continued recognizing the importance of open source tools in science. Recently, you may have seen the first flight of the Ingenuity helicopter on Mars, and that little flight, wonderful flight of this little machine. When the JPL team presented this, I got very excited. This is actually a screenshot from their video where they put up a plot of the elevation of the drone over the Martian surface. This is clearly a Matplotlib window. I actually immediately sent screenshots of this to the family of John Hunter, the creator of Matplotlib, who sadly passed away in 2012, but who collaborated actually with teams at JPL specifically on Mars mission related projects back in 2007, and who had been contributing to Matplotlib for years. And today, GitHub sort of recognizes the role that providing a platform for open source collaboration feeds into science at large. Now, a few weeks ago, we had the pleasure of seeing Jupiter, the IPython Jupiter contributions highlighted by Nature as one of the 10 codes that in their view had an important impact in the history of science. Obviously, for those of us in Project Jupiter who have been doing this for a while, this was extremely satisfying to see, and for me personally, having JupyterCon, our conference, be accompanied by an entire issue of the CISE magazine devoted to the role of Jupyter in computational science and in scientific computing was very rewarding. This was the kind of magazine that when I was an undergrad in physics I used to read, and then when people told me not to work on open source and that I was throwing away my career, as it was explained to me, I sort of never imagined that at one point the publications of our field would recognize that this kind of work had importance. Industry has adopted these tools. So Microsoft made an announcement of their big sustainability and machine learning initiative with their planetary computer that they launched about a year ago. And in their words, the planetary computer is a Jupyter Hub deployment that they manage on Azure with Dask and Pangeo infrastructure, basically, for the analysis of Earth and environmental related data. So we won, right? We're done. Mission accomplished. We've succeeded. Science is open. Well, not so fast. It's not so easy. This is a blog post from a mathematician called William Stein, a fully tenured faculty at the University of Washington, funded by the National Science Foundation, the lead of the Ssj project, which uses Python to basically bring together a lot of open source projects for mathematical research, especially in pure mathematics and number theory and algebraic geometry and combinatorics, and basically said, there's no way I can continue sustaining the development of this open source infrastructure as an academic. I've been on leave, I've been trying to start a company, and I think I'm going to have to resign and leave academic research in order to run a business so that we can have open tools for science. So it isn't so easy, and yet we have an incredible opportunity. Our previous speaker, Dr. Burrell, alluded to a number of these points, that with the kind of open source, world accessible, cloud-based scientific infrastructure we have today, we are sort of at a spot that I like to think about by analogy to the watering hole metaphor in ecosystems. A watering hole is a set of resources that bring together many diverse actors in an ecosystem, some of whom might even actually eat each other or compete with one another in the academic version of that if they encounter each other elsewhere, but they come together because there's a common resource that they all need. And for us, the existence of open data that is accessible under FAIR principles, of scalable computation that we can deploy next to the data, by virtue of the engineering prowess of Amazon, of Google, of Microsoft, of the big cloud actors, and of modular tools that are open and that we can assemble and deploy next to the data and on top of these computational resources, means that we can build communities of practice where multidisciplinary teams that are very disparate, that are very diverse in their backgrounds and their expertise and in their interests, can come together and work on these large-scale complex problems that we have today, like climate change, like COVID, like very rich data analysis. Because importantly, the old download model, download to your laptop and run your data, when our data is on the petabyte scale, is simply unthinkable, right? I mean, if you had a few terabytes of data, you could say, okay, I'm going to have somebody ship me 1 or 2 big hard drives in a padded box, and that'll do the trick. And that is true up to a few terabytes, maybe tens of terabytes even. But when we're talking about 30 petabytes of data, the scale of the CMIP6 data set, for example, forget about downloading that. It's just not going to work. And so we need to consider other approaches. And fortunately, we have today. These slides are courtesy of Ryan Abernathy from the Pangeo project at Columbia. We have the foundations for a scientific enterprise where we move the data, the computation to the data. Our data is prepared in what Ryan calls ARCO formats, analysis-ready, cloud-optimized formats that are evolutions of formats like NetCDF and HDF5, but that are sensitive to the technical specificities of cloud infrastructure. And we use this scalable, on-demand, distributed resources that the cloud mix enables to deploy analysis on these data and using these computational tools. Now I'm going to talk a little bit about what we've done in Jupyter in this space. I like to think of the project that began its life around purely interactive Python usage as sort of an operating system for interactive data science, where the human researcher is very much at the center of the problem, and that human is analyzing data, running code, exploring things, often in the form of notebooks. Some of you, I'm sure, have used at this point Jupyter Notebooks. For those of you who haven't seen it, it's basically a web application that allows you to develop rich documents that combine text and math together with code and results, and that allow you to share those for collaboration and reproducibility. Today, that environment has evolved. What began as a relatively simple web application has evolved into a rich environment called Jupyter Lab, which is much more than notebooks. And I'm going to very briefly show you a little bit of what that is. So for those of you who haven't seen Jupyter Lab, this is a web application. This one happens to be running on my personal laptop, but you could be running this in the cloud or on a supercomputer all the same. You have text, which is entered in Markdown. And when you hit Shift Enter, that text is rendered. You have code that you can execute. That text can have mathematics and LaTeX. And when you hit Shift Enter, they're rendered. And you can also have interactive controls. So the idea is that with one line of code, you can have, let's say, a couple of sliders that allow you to explore the parameters of a model and view a visualization. Now, all of this was already possible in the basic Jupyter Notebook of years ago. What Jupyter Lab offers is an entire architecture for using these tools, using these computations in a variety of ways and recomposing them. So for example, you would like to continue working on your notebook, but you need to see this output that you have over here. You can tear it off, and this output view is still synchronized with the original computation, because these are just two views of one and the same object, but you can continue working over here. Now, notebooks are not the only thing that we have in Jupyter Lab. You can have, for example, documents. And so if you have a Markdown document, you can view it over here, and you can view simultaneously a preview of that document, so that as you are editing the document, and if you put some math, x plus gamma, that math is rendered over here on the side. So you can work in an environment, if you're being remotely hosted, where you have your notebooks, you have your code, but you also have text, documents, Python files, and data as well. So Jupyter Lab has been, let me go back to where I was, has been designed so that all of the tools and resources of the data science workflow are available to you in one place, and you can explore them in whichever format makes sense to you. So let's say that you have a CSV file. This is what a CSV file looks like. This is the classic IRIS data set. But if you open this same data set, you can also view it as an actual tabular CSV render, which is probably more what you would want to be seeing. If you have an image, images can be displayed just as well. But the idea is that these data viewers are yours to customize. So data represents and represents ideas and has meaning to specific communities who make sense of its structure. This is an example of a JSON data file, which if you open it with a text editor looks kind of like this. Just a bunch of nested curly braces, what we're familiar with. We can view it as because it is structured as JSON data. We can view it with a JSON viewer that allows us to see its structure in a little bit of a more understandable way. We can navigate it, we can filter on it. But here we see that this seems to be geospatial data, right? This is geospatial data that has coordinates, that describes museums, for example. Well, it turns out that that same object with the right plugin can be opened and viewed on top of a map. It turns out that this is JSON data, but in the GeoJSON format, which represents geospatial, in this case, the coordinates of museums in Washington, D.C. and downtown D.C. And so if I open, this is the same exact data file that we have here opened, but being viewed in three different forms, right? We're looking at the same data in its raw form, in a slightly more structured format, which is JSON, but without understanding its schema. And here on the right, with a tool that understands the data even better, and basically lets us approach it in any way that that is meaningful to us from an analysis perspective. So the idea is we've been trying to build tools that put in your hands the combination of building blocks for you to do whatever makes sense in your scientific use case. Jupyter Lab ships by default with, for example, image viewers and CSV viewers. It doesn't ship by default with a GeoJSON viewer because that is a bit of a more specialized use case. But the scientific community has developed that. Those for whom that format is relevant have developed these additional tools. And the idea is that this is a basic set of building blocks for you to compose the interaction and data exploration environments that make sense to you, and to extend it in other ways. And folks have developed a variety of capabilities. For example, high-end 3D data viewers that take advantage of modern WebGL in the web browser for sophisticated 3D rendering, connections to robotics, real-time robotics modeling and control, building some effectively a robotics workbench using Jupyter Lab. This was work from the team at Quantstack in Paris. This is a great example not from an earth sciences community, but from the neuroscience community, from a lab at Columbia, the Lazar lab. And I'm going to very briefly show a short video here where what you're going to see is an instance of Jupyter Lab, but you're seeing a 3D viewer of the anatomy of a fruit fly. And these are neuronal circuits in the brain of the fruit fly. And on the right, you see an electrical circuit that simulates that anatomical circuit that was obtained from a CT scan. And that simulation is run on a dedicated GPU cluster. And in addition, genomics data can be pulled about those circuits and about those neurons from a specialized genomics database in the field. But you can still see that this is Jupyter Lab. You see notebooks still there in the middle. So what they have done is they've built a custom analysis environment adapted to their scientific domain, in this case, the study of the neural circuitry of the fruit fly, using the generic Jupyter Lab machinery, using the generic kind of Python computing environments and notebooks, but adding custom tools that are relevant to their domain. And we hope to see a lot more of that. This is a very early prototype. We haven't even released it yet. This is in the alpha releases of Jupyter Lab, but this is a demo of having real-time collaboration. In this case, what you're seeing are two windows, two different browsers. They're just one on top of one another, and two different browsers where I am typing in one and in the other. And the other is synchronizing in real time, Google Docs style, but this is fully open source and fully hosted in your own infrastructure, in the privacy of your own setup, and giving you the ability to collaborate not just on documents, but on code and on any other aspect of your analysis workflow. So this is an early prototype that the Jupyter Lab team has been working on for quite a while. It is ready for you to demo and play with, and it will be included in the next release of Jupyter Lab 3.1 that is coming out soon. And so with these tools, we can deploy resources for large-scale production usage in the cloud or on HPC. This is an instance of our hosts, the NCAR Sizzle team, who make available a Jupyter Hub deployment on top of their HPC hardware. And on the right, we have, excuse me, let me get a bit of water. My throat is a little dry. And on the right, we have a little tweet by Roland Thomas from NERSC at LBNL with the first notebook on the system. And the system was Perlmutter, the new supercomputer that was dedicated last week at NERSC, which is a very large GPU-intensive machine, probably the first breed, the first machine of a new breed of HPC resources that are not only optimized for traditional sort of MPI-style simulation, but also for data analysis and for machine learning on large-scale data. And Jupyter is one of the front ends that makes this phenomenal hardware investment more easily accessible and effectively feel like a really, really, really powerful and really, really big laptop in some sense, which I think is often what we want. We actually want to feel that we're working interactively and fluidly in an environment that is as friendly as our everyday machine, but that just has vastly more power and vastly more access to the kind of data that we're interested in. So this is software that I've been talking about, but Jupyter is importantly a community that builds these tools. It's a complex community. This is a lovely little diagram from the team at the Turing Way, at the Turing Institute in the UK, who have been, and we've been thinking quite a bit about this problem of software, and this was already alluded to by Dr. Borrell in her presentation, that software is a lot more than papers and code. And open source software, using Jupyter as an example, is a project that has other aspects beyond the software. There's services and content. People come often to these tools, not so much because they're interested in building an open source notebook system or an open source server for accessing data in the cloud, but because they want to write a paper, because they want to learn about something, they want to learn how to analyze their data. There's a story, there's an analysis, there's a tutorial that they want to replicate, that they want to share, they want to teach their students. And so we have tools that make it easy to deploy content in the hands of the users, to do your analysis, to share your notebooks. We run a service called NB Viewer to share notebooks that is very widely used for people sharing notebooks on social media. Binder is a related service, but that allows you not just to share notebooks, but entire environments that can be executed using Docker, and effectively does all of the cloud orchestration for you. And in many cases, it's as simple as putting the link of a GitHub repository in the Binder page, and what you get out is a link for that same repository, but in a fully live and executable fashion that you can share with a colleague, so that they can try out your code and your data without installing absolutely anything. That's what that early example from the LIGO collaboration showed. In Jupyter, we've also taken the time to abstract what's below the software. So to say, not only here's an implementation, but here are the ideas that that implementation represents for you to implement on your own. Jupyter began its life as IPython, which was an interactive Python shell at the terminal, but over time it evolved, and the communication between the code execution and the rest of the system was abstracted into a proper protocol, which could be implemented in Julia, could be implemented in R. Those were the ones that we're initially most interested in. They are sort of the three open languages of data science, but by making this protocol an open standard, the community has come out and implemented what we call kernels, basically back-end execution engines, to do this kind of interactive analysis in any of well over 100 different programming languages. And so there's an entire ecosystem that is built not only on top of the code in Jupyter, but more importantly, on top of the ideas and the standards and the protocols of the project. And in order to do that, it turns out that you need people, you need a community, and you need to spend time thinking about the governance, the funding, the decision-making of a community that is very unusual by traditional academic funding standards, right? In Jupyter, my co-director, Brian Granger, who's faculty at Cal Poly in physics, also ex-CU Boulder physicist, and now at Amazon, and I have been working with others in the team in restructuring our governance to better reflect how do you manage something where you have a collection of academics, government researchers, people who represent some of the largest tech companies in the world, like Amazon or Google or Microsoft, and individuals from the community who should have equal voices and who all should have the right to participate and contribute on an equal footing. It turns out that it's a very complex problem, and that cuts across virtually every traditional practice that our institutions are used to funding, recognizing, valuing, kind of fostering, et cetera, et cetera. But I think that this view of open source projects as more than software is actually important, because these services and content are the stories that drive impact into specific communities. And yes, the software is important, but those ideas below the software are what provides the possibility for a broader ecosystem to grow. And the fact that there are people in there that you manage well, for whom you provide career paths, for whom you provide an environment for healthy interaction, is what brings innovation, resiliency, new ideas, new use cases, growth, the kinds of things that a single narrow team working on its own under the purview of a single grant is never going to achieve. Now, I think this impact is important, and specifically for this community in the Earth and planetary sciences, we're seeing wonderful examples of narratives around the Earth built using these tools as collections of notebooks that are then compiled into live interactive books using a tool called Jupyter Book, also developed by folks in the project. And by the way, it goes without saying that everything in Jupyter that I'm talking about is the product of hundreds, if not thousands, of folks in our community who have built it. I am not taking any of the credit of that work for myself. In this case, I'm speaking for a very broad community, both of developers of the tools and folks like Ryan Abernathy and Brian Rose, in this case, who have developed the content. In this case, these are live interactive textbooks. And we're seeing more closer to this community. We have examples at CU Boulder, for example. Leah Vassar and her Earth Lab has a great collection of interactive Earth and data science analysis tutorials and open educational materials that they have been developing. And co-led by Brian Rose from Albany, folks at NCAR have been developing a new project called Project Pythia to build educational materials for Earth and planetary sciences built on this infrastructure with NSF funding. And this is an example of a course on Earth science from UC Berkeley, from one of my colleagues at Berkeley, Nick Swanson-Heisel. And I want to highlight here that in the GitHub repository, it says, if you have a UC Berkeley account, click here. And so this is part of the value of having these kinds of tools be fully open so that we can use them as infrastructure for access for our students. So these interactive textbooks, like the one here, the one from our EPS 88 course, or these from our Introduction to Data Science undergraduate courses, when students click on them, they see these pages that look like basically mathematical textbooks, but they have these buttons that say open on Data Hub. And when students click on that, with one click, they get taken to a live execution page where, using only their web browser, they have that same textbook, but now in a format that they can run without installing anything. And what that makes possible is teaching these kinds of ideas pretty much to the entire campus. So the picture at the top is, for those of you who have been on the Berkeley campus, is Zellerbach Hall. That's our basically our opera theater, our big auditorium for concerts and large graduations. It's not even a classroom, but it's the only place where we can fit courses of the size of Data 8 that have about 1,300 students. By the way, we're not allowed to teach there. That's only the opening lecture. And after that, they have to move online. At the bottom is me teaching on the largest actual classroom on campus, Wheeler Hall, that fits about 750 students. Last fall, I taught the same course and I had 1,200 students. So that one would also not fit even in Wheeler Hall anymore. These are the fastest growing courses in the history of Berkeley. We're reaching roughly 50% of campus media at this point. But we can do so only because we have these open tools that we can deploy next to our students. And those are part of the beauty of that is that these tools are the same tools that researchers are using. I've already mentioned Pangeo. For those of you who are not familiar with it, I want to say a couple more words about Pangeo. It's a project that takes Jupyter, but also other tools in the ecosystem, and deploys them to support this kind of experience for the researcher. So this is a very short video of a Jupyter notebook where Scott Henderson from the University of Washington zoomed into an image. You see some color bars at the bottom, and then the image gets a little bit more refined. What's the big deal? That's like you open a picture in Google Photos, and after a few seconds, it sharpens. Well, it turns out that's about 100 gigs of Landsat imagery over the state of Washington, and refining that means running a distributed cloud engine over all of the different shards of data that assemble that image. And that's what's happening at the bottom. The bottom is the real-time monitoring of the cluster. that uses a tool called DASC for distributed computing and takes in those chunks using Xarray, which is another open source tool for representing effectively netCDF in a Python-friendly way. And the point is that Pangeo assembles this stack to give the working scientist the equivalent of what our students get for this with this, but now for real large-scale data analysis without that scientist having to become a cloud engineer. And Pangeo is a project that has had phenomenal impact in taking this open source stack and bringing it sort of to the doorstep of the working scientist so that that person can focus on their research rather than on becoming cloud engineers. Closer to colleagues that we've been collaborating with, Anthony Arendt and particularly Jessica Schick from UMaine, the development of tools for the analysis of ICESat-2 data. This is a new project called IcePix to download, process, and analyze ICESat-2 data that was developed as a fully open source platform from the beginning, partly prompted by NASA having now an important commitment to more open access and better practices in the development of the tools that are used to access the data from its missions. And so I wanted to highlight this, which I think is relevant in the context of some of the points that Dr. Burrell was making just earlier. So what we're seeing is that with these tools, we can have open scientific infrastructure that is cloud native or HPC native. We saw both supercomputing centers and tools in the cloud, but without vendor lock-ins, right? Because it is important that as we build this infrastructure, it doesn't become Amazon science or Microsoft science or Google science. It should be science, unqualified, and for the community. Those of you who are interested in seeing some more examples of this can go to the Pangeo Gallery, which is a beautiful collection of examples in various fields, from purely technical tutorials on the analysis workflow to specific domain-specific things like analysis of CMIP data or glaciology data, etc. And you can click the links that are there in those buttons in the gallery, or those binder links that I was talking about that allow you to basically go and execute those examples without installing anything. Now, this open infrastructure is being adopted in many places. As I go through a couple of these examples, I have found them to be illustrations of how elsewhere in the community, others are similarly saying that with these tools, we can access the kind of data that is relevant to our users without being confined to what any particular company or commercial product is trying to build. So this is an example. I'm not connected to this person at all. I just found it online, and it was interesting to see how she was building a portal to expose for live analysis a lot of open data that the government in Austria provides. And this was, I guess, data about Vienna. In Canada, Jim Colliander, in partnership, who is the former director, he just stepped down, of the Pacific Institute for Mathematical Sciences, partnered up with both Cybera, which is a nonprofit in Canada, led by Barb Cara, and with the Compute Canada organization, which is a government organization that provides HPC resources for Canadian researchers. And between Cybera and Compute Canada, they've provided two separate projects, one called Callisto that offers basically Jupyter hosting for K through 12 educators, and Ssj that offers similar resources, but for researchers on top of HPC and large-scale cloud infrastructure. So with these tools, they are providing in Canada effectively this kind of infrastructure for everything from kindergarten to supercomputers for researchers. Other communities have built other more customized environments. These are two examples in bioinformatics. The Gene Pattern Notebook is led by Jill Messerov and her team, formerly at the Broad Institute and now at UC San Diego. And KBase is a large-scale DOE project led by Adam Arkin at LBL and UC Berkeley, and colleagues at Oregon and Brookhaven and Oak Ridge, who have built environments using the Jupyter infrastructure to do sort of in-depth, large-scale hosted analysis of genomics and bioinformatics data in their respective communities. And finally, at the European Union, the Joint Research Center, which is a large-scale research facility jointly funded by various EU agencies, including the ESA, has been building what they call the JEODPP. I have no idea; it's a complicated acronym, but they do wonderful work on building very sophisticated plugins and analysis layers on top of Jupyter Lab, precisely realizing, I think, this vision that I was mentioning earlier of using it as a foundation for domain-specific analysis tools that impact their community on top of the data and infrastructure that is relevant to their users, and they're doing really a phenomenal job. But back to the story that, well, this is important, and we're seeing all of this value in research and education and infrastructure that powers big projects, but we have the cautionary tale of William Stein, and it turns out that what we have is what a term that I credit Tracy Teal with, which is catastrophic success, right? We have succeeded in replacing many proprietary tools. This article from 2015 had analyzed the citations of IDL and Python in the astronomy community, and was seeing the growth of Python taking over IDL. But it turns out that tools like IDL and MATLAB and Mathematica and others are not. I'm not here to demonize them in any way. I've used several of them extensively. And one important point is that they had an economic model, right? By paying for these tools, we were also paying for the time of engineers and researchers and salespeople and tech support people, et cetera, who actually provided important roles in these projects. And open source doesn't have that. And open source is not magical fairy dust that fixes these problems automatically. And there's a deep contrast in the culture and incentives of open source and of traditional academic careers, funding, reward, tenure, promotion, hiring, et cetera, et cetera. I'm not going to go through each one of these points in detail. We do not have the time for that, but I put them up here to sort of tickle your brains a little bit about the contrast and what we are doing with a culture where all of our funding and incentives and sort of stable processes are in some ways at odds with the flow and processes that are leading to what our infrastructure looks like today. So it's wonderful to have this software infrastructure. It enables all of this promise that I've tried to highlight in a variety of ways, but it is very much at odds with how our culture, our fields, our careers function. And there's no easy answers there. There's an unfortunate incentive in academia, in the chase. Remember those important words in your NSF proposals, that they have to be novel and transformative. You build yet one more attempt at that thing that the other people who were not novel and transformative didn't quite build, and yours is going to be that much better. And we have a lot of that. We have a lot of these. New half-built roads that take us to the exact half-finished spot as the old ones before us. We run out of budget, and we don't actually quite complete them. In this sense, the Pangeo project is a wonderful example of refusing to do that. And I want to highlight a blog post that they wrote about a year and a half ago, where they said our pattern is to reuse, integrate, document, demonstrate, and contribute back upstream. So to contribute to DASC, to X-array, to Jupiter, et cetera, rather than saying we're going to claim to rebuild something just so that it's new. Instead, wherever we identify something that was doing something useful, we will contribute back. We will credit those people. We will instead use what they did. And if necessary, we will bring it and document how to use it for our use case. We will demonstrate to our community how to best meet its needs, et cetera. And I think this is a much healthier pattern, even if it appears to buck some of the immediate incentives and patterns of our field. So we need organizations and projects that have this kind of human and technical culture. We're trying to do that with Jupiter. We're deeply connected to Pangeo. NumFocus is a nonprofit that I was part of co-founding that tries to be an umbrella for a lot of these open source projects. I want to flag that the Chen Zuckerberg Initiative, with their Essential Open Source Software for Science program, are doing an incredible job of providing not just funding, but actually funding that is mindful of this entire spectrum of challenges and issues that range from accessibility to diversity to community facility management to project maintenance, all the way down to, yes, the kind of nuts and bolts of the technical ideas. And I would love the federal agencies to model more of their programs after the kind of work that the CZI team is doing. In my introduction, they mentioned that I'm part of co-founding a new initiative called 2i2c.org that tries to be a player in this space. It's a nonprofit organization. It's actually not a standalone 501c3. It's currently hosted under an umbrella organization called the International Computer Science Institute at UC Berkeley. And this was co-founded with Jim Colliander, who I already mentioned, Lindsay Hagee, another faculty member at UBC, Ryan Abernathy from Pangea, who I've mentioned, and 4 of us at UC Berkeley, Chris Holgraf from Jupiter Book, Catherine Carson is a professor in the history department, and Yuvi Panda is an engineer who runs a lot of these hubs that I mentioned for education at Berkeley. We tried to create an organization that would manage infrastructure, because it turns out that running hubs for thousands of students for distributed research communities is not the kind of thing that an academic is really well suited to doing, but we don't want to cede this space purely to commercial interests. So we believe it's important to have a research and education entity that is playing a role and is advocating for the needs of scientists, for the needs of educators in the space, and can partner up with educational institutions, research funding agencies, and research labs in the management of infrastructure, and who has a mission to do research and development of the tools and to support the open source community in a sustainable way back. So 2i2c is committed not only to being fully open, but to actually doing some of the things that I mentioned in these Pangea principles of putting all of our effort and resources back into the sustainability of the open source environment that we draw from, rather than in building our kind of a new silo for corporate profit. Jupiter has received funding and resources, and we're extremely grateful for that. But the question is, how about everything else? What about the other projects? And I would like to make the case that the bang for the buck of investing in open source software should be spectacular. The federal R&D budget in 2018, last I checked, was on the order of $180 billion. If we ask what fraction of R&D today depends on computing, like think of how much science is done without computers today. Is 10%, 30%, 50%? I mean, I would argue that probably more than that is critically dependent on computing. And as we've seen, more and more of that is open source. $200 million is on the order of 0.1% of the budget, 0.1%. And well spent, 200 million annually would have a major impact. I already mentioned the CZI EOSS effort, and it is having a wonderful impact in our ecosystem, and its budget is a fraction of that. So the federal agencies, if they spent it well, could have an important impact. Well spent, however, means understanding what are some of the features of these successful, resilient, impactful projects that are not the kinds of things that have gone traditionally into things like NSF and et cetera solicitations. So broad community engagement, well-managed pipelines for new contributions, proper planning, recognizing that writing the code is only a small part of the job, and understanding that these projects need to be treated like new kinds of organizations with complex needs. And that having a proper strategic vision for these projects requires professionalization. It requires that we recognize all of this work as full-time work at multiple levels in R&D, in operations, in community, et cetera, and that recognizing this is actually being inclusive. So up until now, we've had a lot of, on the one hand, throw away what they call professorware or studentware, software written for the purposes of getting that paper out or that thesis out and nothing else. And therefore, only those who can afford to do that end up contributing. And on the other hand, if we properly recognize and pay for this, more people who need actually to have a job can participate. So we're not relegating the opportunity to be part of this ecosystem only to those who can. So in closing, I want to leave you with a link to a new paper that came out, published by Kjell Gentleman from the Meridional Institute and folks like Ryan Abernathy, precisely about these ideas, and that kind of wraps a lot of what I've been saying into a very nice package. It just came out in AGU Advances called Science Storms in the Cloud. And it precisely, these are just a couple of tweets from Kjell and from a climate scientist looking at basically doing analysis of CMIP data, some of the largest data sets that we have today, on a $30 Raspberry Pi, and Julius in this case on his phone, to access tools that can analyze this kind of data at scale in the cloud. And so let's think about these questions. Let's think about economic models, governance models, career paths, these kinds of structures, and how do we fund them so that this promise can be realized in a sustainable manner. So thank you for your attention. This is a link to these slides if anyone is interested. And if we have a couple of minutes, I'd be happy to take some questions.
Fernando, that was absolutely awe-inspiring. These are things I'm trying to learn, you know, so that we can better support our community. And this was very perfectly timed, at least from my vantage point as a agency bureaucrat. I'm going to pass it on to Erica, who is the moderator and has, I'm sure, lots of questions. We can't hear you, Erica.
Sorry, I had problems with the muting again. I was saying, in fact, I do have a lot of questions. Thank you, Fernando, very much for your talk. And I will just go ahead and start asking. So I will combine together two questions about the definition of open science. So the first one is actually, can you define open science and how far does it reach, or what all does it entail? And are there any boundaries of open science, or like some areas where there are restrictions or like openness? So yeah, it's a big question about the definition of open science mostly.
Yeah, that's a very good question. Thank you, Erica. It's obviously a little bit philosophical, and I'll probably give a somewhat imperfect and incomplete operational definition, which I think of open science as science whose ideas and results and practices are enable whenever possible, and I'll qualify it to go to the second part of the question, but whenever possible and as much as possible, the participation of others in the community with as minimal barriers as is absolutely possible. And that means access to the data, access to the tools, access to the results, and access in a way, but because for me, open science is not simply, can you get the PDF? Can you get someone to give you the PDF? But more importantly, can you build upon it? Can you query it? Meaning, can you re-execute that? Or do you have to blindly trust? Having access to a PDF that provides an incomplete description of methods, no access to code and no access to data, in my mind, well, it's better than a paywalled PDF, but it's actually not that much better. So it really is about enabling others to build upon what you did. Now, that doesn't necessarily mean that you have to ship 30 petabytes of data to everyone. There's reasons where in some cases it's legitimately difficult to replicate everything, but we can find ways to gradually lower those barriers. So you can, for example, say the raw data, let's say in the cases of big particle physics experiments, you can't download all the data for the Higgs boson, but some of the later stage data can be reanalyzed and re-executed. So if you plan for stages of access or cases where you have, for example, in biomedical research, individual privacy constraints on the data, you may still find ways of making the data, the results, the computations accessible to others. So it is very much about the intention that you place and the processes that you put in place for others to be able to build upon your work, even if you have to recognize that data size, model sizes, hardware access, etc., can impose sometimes some limitations. So I'm not an absolutist in that sense, but I think it is about enabling collaboration.
Thank you very much. And actually, to connect to the huge amount of certain data, I had another question on that. Considering the push to higher and higher resolutions, should we be moving away from disseminating data via files? Because obviously these files are starting to become very big. So for example, accessing simulation as digital twins that are mirrored on the cloud to be analyzed in real time.
I think there's going to be some of that. So there's two things. On the one hand, even what we call files, I think, is changing. We've all seen, and we probably all have lying around examples of code that is where there's a huge pile of name and directory mangling and file name pattern matching, where a lot of metadata is effectively encoded and semantics are encoded in your directory layout and your file names. Kjell Gentleman, who I already spoke of, has some very lovely recent tutorials on how to move data processing into the cloud and move away from manual file management into metadata catalogs that describe entire collections of data in a slightly more abstract fashion. It takes a while to get used to moving from the download a bunch of HDF5 files, knowing where you have them on disk and munging them, to saying, describe this global data set with this approach and analyze it a little bit more as an opaque object. But once you make the transition and once you prepare the data for that, and Ryan Abernathy has some great tutorials on that preparation process, it can actually help you scale better. So this is still in the domain where there is data. So I haven't gotten to the complete question, but I think transitioning from the manual file management more to a dataset object mindset. And I think these are some of the points that the Pangeo team has been making, and they illustrate how to actually do that in practice and the benefits of that. Now, the next question is, what about just not having the data at all and simply having the models? I think that is legitimate. I have heard a similar pattern in the bioinformatics community where people have told me that at this point, in many cases, it's better and cheaper to resequence organisms or resequence samples than to have access to the sequencing data. Because honestly, the cost of sequencing, of genomic sequencing, has gone down so much, and the speed of doing it has become so much faster than it used to be, that in many cases, they don't even keep the data around. They just say, well, if we need this again, we'll just grab a sample again and throw it in the machine again and get the data when we need it. That's the biological equivalent of what the question was asking. And I think that's a legitimate tool. We'll have to see kind of where things are, but I do think there is going to be cases where that may make more sense. Just give me a one-click thing where I have access to the Docker container. I choose the parameters and the size and whatnot. I know it's going to cost $20. I click and I run it and I get the results exactly that I need. It's a little bit of sort of just-in-time manufacturing for scientific data, but I do think that can be a legitimate pattern. Maybe not replacing, but adding to our toolbox.
That's very interesting. Okay, one very quick thing. So because I saw at the end of your presentation that you put a link to your slides, and someone actually explicitly asked for them. So maybe we can also copy it.
I will copy that link. I will happily copy that link and put it on the chat.
Yeah, and then we will copy it on Slack. Thank you very much. Let's go to questions again. What lessons from your courses at Berkeley have you learned about the small steps that students find most helpful to build open science skills?
So two things. One is the fact that, and this is very biased, I'm not citing comparative research or anything, I'm just kind of like ad-libbing from my hands-on experience, if you will. One is the fact that we teach these courses with the real world tools, right? The students are learning, and they really appreciate that. They're learning with real world data sets. They download them from the internet. They're using Pandas, they're using Matplotlib, they're using Plotly, they're using Jupyter. So the tools they're learning with are not toys, classroom toys, where when they go out in industry, they're going to find themselves with something completely different, or in research, whatever career path they follow. And that is extremely valuable to them. And they really appreciate that. I just finished teaching a course on reproducible research this term that wasn't that big when it was a small course for like 60 student class. The whole course was run on GitHub. The students had to do their work as open source collaborative teams collaborating on GitHub. And we got many expressions of gratitude from the students of saying, these skills are incredibly valuable and we're not learning these anywhere else. And the other part of that, which it's kind of related but not exactly the same, is the fact that they learn computational practices, some of which have been taught in places like the carpentries, which some of you may be familiar with. But this notion of learning, it's not so much learning about algorithms, but it's learning what is testing, what is documentation, what is version control, what are all of these practices that actually support that you do the right job. And I have had multiple students come back to me. I'm actually going to be teaching in the fall, and the student said, I want to give a lecture back to your class because I learned so much with these things and it has helped me so much in my career that I would like to give a guest lecture. And I actually told the student that would be wonderful. Our students would love to hear from somebody who took the class 2 years ago, how that has benefited them in industry and has propelled their career. So those are kind of the two that come to mind.
Thank you. Another question. Is there already a Python open source for computational physics? Yes, and we will stop there, and then I will do another one later.
So there is. So for computational physics, there is a classic textbook called Computational Physics by Landau, Pais, and Bordenau. This happens to be, let me put the slides here. So this textbook, Computational Physics Problem Solving with Python, is a textbook that I actually have a deep personal connection to this textbook because one of the co-authors, Manuel Pais, was my mentor in undergrad in Columbia in physics 30 years ago. And they wrote this textbook that has gone through a few editions. It's called Computational Physics, but they do have online the GitHub repository for all of the notebooks. So you can actually see and execute all of that code. It's kind of a classic computational physics textbook. And they put them up a few years ago up online. And actually just last week I did a quick experiment, and I need to email them. I did a quick experiment of turning this repository into one of these Jupyter book textbooks that I was just showing, because I ran it locally. It took me 10 minutes to do that build, and I think it would help make it a little bit more readable. But you have in here notebooks that have all of their code and all of their analysis in a sort of traditional teach computational physics end-to-end kind of thing. The chapter I clicked on was error and uncertainties in computations, and here you go, right? And this textbook actually has on their website, it has videos for all the lectures. So they offer the textbook with a complete collection of lectures. You can buy it on Amazon in paper, you can execute it online, and you can view the lectures online. There's probably more, but this is one that comes to mind, and it happens to be very meaningful to me because one of the authors was my former undergraduate mentor.
Very nice. And now I have a literally $1 million question.
Okay.
How do you get funding for open source projects?
Well, that was in a sense the crux of my talk. In Jupyter, we've been fortunate that some private foundations were critical. The Moore Foundation, the Sloan Foundation, both of those funded us early on. Our first large grant for Jupyter from the Sloan Foundation came to us in 2012, basically because of some visionary program officers at these foundations. And so these private funders, Sloan, Moore, Simons, Chen Zuckerberg, and now Schmidt is also funding Jupyter, have been absolutely critical in recognizing the value of open source as critical infrastructure. And I did highlight this particular program from the Chen Zuckerberg Initiative right here, Essential Open Source Software for Science, that is funding, I think, AstroPi, I think SunPi, the heliophysics project is being funded by them, I believe, along with many others, even though their original mission was in biomedical research. But I think the federal agencies are changing. I participated in an OSTP event a few months ago where I made some of this case. A version of these ideas was originally developed for a talk I gave at NSF headquarters before the pandemic. And I think I do have a brand new grant from DOE. So Oscar, the DOE computing division, is funding some Jupyter because, as I showed, Jupyter is now the portal for their biggest new supercomputer at LBL. So I think the tide is changing, and I'm hoping we can make this argument in a coherent way to the funding agencies so that there's more resources that are put into this, because that's the argument that I tried to make at the end, that it actually is, on the one hand, there's high risk in basically building our infrastructure of high-profile projects like LIGO and EHT on top of stuff that isn't funded and that has no economic model. But on the other hand, I do know that agency officers recognize these issues. They're not blind to them. They are very interested. And I hope we can partner and learn from the experiences of what has worked well to get more resources. So 12, 15 years ago, this was a nightmare making this case to funding agencies. And I know because I wrote grants for this stuff in 2004. And they basically they were like bugs on a windshield. But today there is recognition and interest and participation of the funding agencies. And I hope if we continue these conversations, it will get better. So I want to be optimistic on that front.
Hey, Erica. I want to make a comment on this because this is really important, Fernando, in the way we kind of anticipated this virtual workshop would work is that we will take some of our sort of salient questions, try to create white paper out of that. Heliophysics division is coming up for its next decadal survey. And I think what you are talking about, it's more revolutionary than I have heard, kind of bringing everything together. That overarching kind of view is really necessary when we formulate our plan. So I would really appreciate your staying engaged with our both, senior, mid-career, early career folks as we try to develop kind of our future plan or white paper. And sorry, Erica, for jumping in, but I'll let you get back to more questions.
And Madhulika, absolutely. I just want to say briefly that yes, I'm interested. I'm actually working on a white paper on this topic, and I'm absolutely happy to engage again. This is really important, I think, at this stage. So thank you for saying that.
Thank you indeed. I'm lost for a second. Yes. Okay. Question: what are the best examples of organizations and projects with the right human and technical culture?
So obviously, I'm very biased because I haven't done a systematic survey. There are folks in this initiative in Chan Zuckerberg who have probably a bigger and better view of the ecosystem. But I think Pangeo is a project in the earth sciences community that I like a lot in that regard, precisely because they've taken a very participatory and collaborative view, right, of the problem, and this idea of contributing back upstream to the ecosystem that feeds them has been extremely valuable. I am not super close to it, but I do know that the AstroPi project in the astronomy community is a very, very well managed project. Kelly Cruz, she's faculty. I forget where in upstate New York. I'm sorry. I don't work with her closely, but I know Kelly Cruz is one of the leads of the project, and she has done a terrific job in kind of managing the funding and the community culture for the AstroPi project to be quite inclusive. I want to flag that the scientific Python community, this URL right here, scientific-python.org. This is a new effort, actually led by a couple of colleagues of mine at UC Berkeley, where what they've done is they've created this steering committee of people across scientific Python projects, right? These are people who are, it's not SciPy, it's projects across the ecosystem of scientific Python tools to try to develop a cross-project kind of strategic vision, coordination, and collaboration initiative across the individual projects. And I think initiatives like this will be very valuable in helping precisely create a better culture, especially coming from projects like AstroPi, like NumPy and SciPy, like Pangeo, that are doing a good job and kind of infusing others with good practices and coordinating and collaborating. So those are some that come to mind, but again, this is just off the top of my head, so it has every possible bias you can imagine of just the things that are kind of top of mind for me on a regular basis.
Thank you very much. And with this, I think I turn back to Lika.
Thank you so much for the opportunity to speak. And I will stay on Slack for a little bit in case there are other questions. I just joined the Slack channel, so I appreciate the invitation and the opportunity to speak. Thank you all.
Thank you so much, Fernando.
And now for the last talk of the morning session, we have Ryan McGranagan. I always pronounce it wrong somehow, even though it's not particularly difficult. Mine might be more. Ryan, now he's another one. One of the advantages of being in a field for a very long time is that I have met so many of you, and yet there are, as we make these heliophysics more and more cross-disciplinary, interdisciplinary, there are newer people we are meeting. So I met Ryan close to a decade ago. He became one of our Jack Eddy Living with a Star postdoctoral fellows and went to NASA Jet Propulsion Lab, during which he studied the Earth, solar system, planets, interactions with the sun, and visiting faculty position at Dartmouth. But he got his PhD from CU Boulder. Like many of the people here, it seems like Boulder is almost that focal point. I mean, even Fernando, right? I mean, we didn't choose people in this manner, but it is kind of interesting to see the connectedness. Now, Ryan is presently the principal data scientist and aerospace engineering scientist at Astra Associates in Boulder, Colorado, where he leads data science and machine learning efforts to improve our understanding of the Earth space environment. Now, Ryan and I have also worked with other areas like in Frontier Development Lab, which is a research accelerator, and you'll hear a little bit about that from one of the speakers later in the session. One important aspect about Ryan is that he takes really a multidisciplinary approach to anything he does. And, that alone sort of connected us. And I really resonate with these ideas. And he has kind of called this an interdisciplinary approach to the study of space, bringing together traditional space physics with innovation from the field of data science. And he's going to kind of tell us more about the parallel session goals and give us an overview on that. So Ryan, please.
Thank you, Lika. It's a very kind introduction. I'm humbled to be following the morning speakers. Each one was inspiring, and I don't know about everyone else, but I have notes upon notes for myself to follow up on. So thanks for an inspiring morning to everyone. And what I wanted to do, I'm not going to take this full 30-minute period because I do want to give everyone, all the participants, a moment to really look at the afternoon opportunities available. There's going to be 3 different ones, and make sure that you have some time to look through those to decide where you want to be. But what I did want to do was kind of recollect after this morning and understand how what we're doing this afternoon links to the talks that we've heard and the posters that we heard yesterday. And I wanted to start here because this is a cross-disciplinary symposium. And so I wanted to start with that ethos. And the quote that kind of keeps me grounded in this was something that Norbert Weiner wrote in his, what I think is really a pivotal work called Cybernetics from the 60s. I think that work really shifted the ground beneath the feet of scientists and thinkers and kind of rendered the barrier between what is known and how we can know it more insignificant than it ever had been before. And he writes that the most fruitful areas for the growth of the sciences were those which have been neglected as a no man's land between the various established fields. And so I think that kind of speaks to a lot of what we're trying to accomplish with this workshop. You see that we have speakers who are domain focused, who have come from the space physics, heliophysics side in particular. You see people who have walked between fields, between earth science and heliophysics and space physics and planetary science, all the way over to this new emerging field of data science. And we've been blessed to have a lot of great talks on that already. What we're going to try and do this afternoon is bring all those things together. And I'd like to relate it to kind of the more focused area that we're thinking about is the intersections between earth science, planetary science, astrophysics, and heliophysics, and trying to understand how we can better interact with those communities. And in a lot of ways, data and the computational models that we use can be the common language across those. And just to remind us of what we're doing here, I like to keep this quote in mind from the former NASA chief scientist, Walid Abdelhadi, about what it is we're actually doing within NASA and within these sciences. And he said that NASA science really is the manifestation of all that makes us human. And so that's always been an inspiring quote to me, and I hope that it can be inspiring to you as we move into the afternoon. So what we're going to be doing is kind of going back to something you heard Rajesh Gupta introduce yesterday, and I think Fernando reiterated a few of these items, that data science really needs a domain. So data science itself is not a discipline, but it's something that needs a discipline. And applying data science is about the practice of this. So actually using the tools, and as Fernando mentioned, not just tools that are meant for the classroom, but tools that you can learn with to take beyond the classroom. And so what we've done is designed something that's an uncommon component of this workshop, that are these afternoon parallel breakouts. These breakouts are designed to allow each of you to take the excitement that you have right now and the ideas flying around from all these plenary sessions and apply them, to step into the practice of them so that you can embody these ideas and develop some experiential learning around them. So I'd like to take just a few moments about how these sessions will be run to give you an idea. So first of all, there's a few objectives that we kind of set forward as a coordinating committee for this. The first is really the overarching objective of the whole workshop, which is to identify and promote novel opportunities for each of you to take advantage of these new techniques that are coming from computational and data science. And those include machine learning and AI techniques. So we don't want these sessions to be just conversations and presentations, but really the practice of them. And so that's what these afternoon sessions will bring. Then the third objective to this is to gain exposure to and experience with the tools that we're talking about throughout the morning sessions. So a few thoughts from me and the organizing committee about what you should do. I think you should be very open. Just kind of make sure that you have the time to focus on these tools and these learning sessions. These are really uncommon opportunities open to you. Make sure you ask questions. The people leading these sessions are particularly helpful and they're thought leaders in this space. And so you have an excellent resource available to you in these individuals. Struggle through the material. This is the best way to learn. So pick these up. I encourage you to be very active during these sessions. I know it's difficult when we're not sitting in the same room looking at the same computer screen to do this, but I think we can kind of set a precedent for how things can be done in a virtual setting. Try to find aspects of the work that you're doing that these tools will be applicable to. We're going to have another session of this workshop or this symposium next year that's going to be in person. And so that's going to be an excellent opportunity to kind of let the ideas that we're putting together now cultivate and build towards that next symposium. And then following along that same line is find others that might have similar interests to yours and form working groups that you can maintain throughout and beyond this workshop and really spark new research vistas. That's probably one of the most important things that we can do today. So I also wanted to set a few expectations. I don't think that these necessarily need to be said, but I do like to reiterate them so that we have appropriate behavior. Be respectful, be direct, but also professional, and really encourage discussion. So we don't want to discourage people from speaking and being a part of the conversation. So be welcoming to people and be inclusive, and understand that there will be different perspectives. And then finally, appreciate and accommodate all similarities and differences. I think these are important behavioral components. And then as in terms of participations, we would like you to keep track of some of the questions you have. I think these are very valuable in how we will move forward from these sessions that we're running, and help these 2-hour sessions be a springboard to continue the process. So try and be an active member to those conversations. This is a quick look at what the agenda will be. I'm only going to take another few minutes here, and then I'm going to give you 15 minutes to really choose your breakout, at which point you can join the breakout session and start to interact with the tools. I would ask that you try to pull back from the tool towards the end of these sessions and try and synthesize a little bit about what you've learned, so that we can crystallize that and take that forward into the following days of the symposium and beyond. This is a quick look at what the parallel sessions are for today. You can find all lists and information about these parallel sessions in the agenda for the symposium. We'll hear from Wojciech Samek about explainable AI. This is one that I'm extremely interested in, and Wojciech is particularly suited to this as he's written a textbook about explainable AI, so quite topical. ASTIBot has been leading one of the frontier efforts to create open science for our geophysics community. And so it's called NGeoResin, and you can learn a lot more and start to get some experience with some of the tools that Fernando was just talking about, Python and Jupyter Notebooks. So that's an excellent opportunity as well. And then Andrea will be talking about end-to-end approaches for predicting geoeffectiveness. So really applying some of these tools to the data that matter to us. So I am personally excited about all of these. I hope that people will take advantage of them. And the parallel sessions tomorrow will be distinct from these. And so I encourage you to look at the agenda to see what those will be. With that, I will give you the few minutes to do some exploration of these different parallel session breakouts. Thank you very much.
A quick question, Ryan. We still have a break, correct?
I believe that's correct.
Yeah. So this is going to start at 1 p.m. Mountain Time.
Right. Yeah, I think maybe I didn't have time.
Samiko. Erica, I don't know if there are questions for Ryan. I'll let you.
I was saying, no, I mean, he just explained what's going on later on. So yeah, no, there are no questions.
If not, then we get a little extra few minutes. I think this session was supposed to run till 11:30. It's 11:13, so please enjoy that time. And then see you back at 1 o'clock in one of the sessions. Thank you very much to all the participants from this morning. It's kind of hard to imagine, we have maintained the momentum from yesterday to today. It's been quite riveting. A lot of new things we are learning, and some of us have grown up in this field for a long time. So it's exciting time. Thank you.